Good evening and welcome to The Whispering Scientist. Thank you for tuning in tonight, whether you are listening tucked beneath warm blankets, drifting on the edge of sleep, or simply letting your mind soften after a long day. Before we wander too far, this quiet journey is all about the hidden states of matter, the strange and gentle ways the universe arranges itself when conditions become extraordinary. While you're getting comfortable, I would love to know where in the world you are listening from. It is always soothing to imagine these calm science evenings stretching across continents and time zones. And if you feel relaxed enough, please do leave a like on the video and consider subscribing if you're not already part of this little nighttime community. For those who are already subscribed, thank you so much for being here again. If you would like to hear the next sleep-friendly exploration as soon as it arrives, a gentle tap on the notifications bell will make sure you do not miss it. I will try not to make this journey so interesting that it keeps you awake, but if your thoughts do happen to wander inside the story for a while, at the very least you may drift into dreams with one or two new ideas floating softly in your mind. So as you settle in, here is something to wonder about. If matter can behave in ways we rarely see, what might be hiding beneath the ordinary world you touch every day? The familiar states you live in are only part of the whole picture. Solids, liquids, and gases are simply the most convenient costumes matter wears under gentle everyday conditions. But beneath those simple shapes lies a far deeper landscape, one shaped by temperature, pressure, and the quiet rules of quantum behavior. When matter is pushed to extremes, it begins to reveal personalities that are all but invisible in daily life. Some states emerge only near absolute zero, where motion slows to a near stillness. Others require the heat of stars, the pressure of giant planets, or the brief flashes created inside powerful scientific machines. This journey is an invitation to drift through that hidden landscape slowly and peacefully, discovering how matter transforms when its environment changes and how each state reveals a different layer of the universe's character. By the time we finish, the everyday world around you may feel a little more mysterious. The world around you feels calm and familiar, shaped into objects that hold their form, liquids that settle softly into their containers, and airy spaces filled with invisible breath. These states of matter are so woven into daily life that it is easy to imagine them as simple permanent categories, as if solids, liquids, and gases are three tidy boxes nature uses to organize everything it makes. But when you drift a little closer, when you let your attention rest gently on the subtle behavior of matter, these categories begin to soften. They blur at the edges, shift with temperature, rearrange with pressure, and reveal complexities that are far more delicate than their names suggest. A solid, for instance, seems utterly unchanging from the outside: the table that holds a book, the stone beneath a shoe, the glass set carefully on a shelf, each appears still, steady, and unbending. But within that apparent stillness is a quiet world of ceaseless motion. The atoms inside a solid sit close enough to brush shoulders with their neighbors. They rest in orderly arrangements, forming neat repeating structures that spread out in all directions. Each atom trembles gently, vibrating in place, never straying far from the pocket of space it calls home. If you could shrink yourself until the atoms were towering around you, their vibrations would seem like a soft murmur, a constant background hum that holds the entire solid together. These repeating structures are the reason a solid keeps its shape. Each atom's position supports the next, creating a stable pattern that resists the small disturbances of daily life. Yet this orderly arrangement has its own personality, responding to changes in its environment with quiet sensitivity. A warm morning can loosen the bonds between atoms just a little, allowing them to vibrate more freely. A cold night can tighten the structure, drawing the atoms closer until the solid contracts by a small but measurable amount. Even a seemingly rigid material is always in gentle conversation with the world around it, shifting in ways too small for the eye to notice. Liquids loosen the pattern. Their molecules remain close together, but they no longer hold fixed positions. Instead, they glide around each other, drifting and weaving like a slow, fluid dance. In a glass of water, every molecule is constantly rearranging itself, sliding past its neighbors, forming and breaking bonds in the blink of an eye. This freedom of motion gives liquids their softness, their ability to flow, and their tendency to settle gracefully into the shape of whatever holds them. At the surface of a liquid, the story becomes even more interesting. The molecules there cling to one another with a little extra strength, forming a delicate, flexible film that gives rise to surface tension. It is why a droplet of rain beads on a leaf, why a calm pond forms a mirror-like surface, and why some insects can walk or rest upon still water as if it were stretched silk. Though we often think of liquids as shapeless, they hold more order than we give them credit for and more structure than their flowing nature suggests. Gases, by comparison, are the wanderers of the matter world. Their particles spread out widely, moving in long, free paths until they bump gently into one another, or into the boundaries of the space they occupy. A gas will expand to fill any container, not out of ambition or pressure, but simply because its particles drift wherever space allows. To the naked eye, gases appear empty. But if you could follow a single molecule of air, you would see it moving in a gentle zigzag pattern, bouncing from one invisible encounter to the next. Because the particles in a gas are so widely spaced, gases are easily compressed and easily expanded. Warm them and they begin to move faster, spreading out, creating more pressure. Cool them and they slow down. Their behavior shifts so smoothly that you might never notice the quiet negotiations happening among the particles. This responsiveness is one of the reasons air carries sound, stores warmth, and allows life to breathe easily. The transitions between these familiar states are where matter becomes most fascinating. When a solid warms, its atoms gather enough energy to break free from their fixed positions. The once rigid structure loosens, and the material begins to behave like a liquid, rearranging itself more freely. When a liquid cools, its molecules slow and settle into orderly patterns, returning to the stillness of a solid. Yet, these transitions are not sudden, clean breaks. There are slow rearrangements, subtle shifts in motion and spacing that unfold gradually layer by layer. Even gases, when pressed closely enough or cooled sufficiently, can transform into liquids through an equally graceful process. Near the boundaries between states, matter behaves in ways that do not quite belong to any category. A substance nearing its boiling point can form shimmering surfaces that appear solid for a moment before collapsing into liquid motion. A liquid near freezing may thicken and slow, becoming almost glass-like, before finally settling into the stillness of a solid. There is also a hidden region where the distinctions between liquid and gas dissolve entirely. Under the right pressure and temperature, a substance can enter a supercritical state, sliding into a form that is neither fully liquid nor fully gas. In this condition, the substance moves with the ease of a gas, but carries the dissolving power of a liquid. It slips into porous spaces, swirls freely, and behaves in ways that feel almost uncanny. It is a reminder that the boundaries we draw between categories are conveniences, not fundamental truths. Even the ordinary world you see each day hides unusual behavior near its extremes. At temperatures very close to melting, solids can soften and rearrange slightly, bending light differently, or changing texture without appearing to melt. In a deep cold, liquids can become sluggish and syrupy, almost holding their shape as if caught between flowing and freezing. Gases under immense pressure can begin to act more like liquids, clustering closely until their movements grow more coordinated. Once you see how subtle these transitions are, it becomes clear that the classical states of matter are only the simplest versions of what matter can be. They are the familiar faces that rise naturally under everyday conditions, but they are not the full story. Just beneath them lies a far more intricate landscape, one shaped by extremes of temperature, pressure, and the quiet rules governing particles. These first states are merely the doorway, the gentle introduction to a universe filled with hidden behaviors waiting to be explored. When you look up at the night sky and see a star shining softly in the darkness, you are watching the most common state of matter in the entire universe. Not a solid, not a liquid, not a gas, but something warmer, freer, and more energetic than all three. It is a state born from heat so intense that atoms can no longer hold themselves together. The electrons that once circled quietly around their nuclei drift away, leaving behind a sea of charged particles, all moving with a restless shimmer. This is plasma, the state that fills the sun, lights up distant nebulae, forms the graceful glow of the aurora, and flashes briefly across the sky in the branching paths of lightning. Plasma begins where heat overwhelms the ordinary structure of matter. In a gas, atoms wander freely, bouncing gently from one collision to the next. But as temperature rises, their movements grow more energetic. Eventually, the collisions become so forceful that electrons are knocked loose. Once enough electrons have escaped their atoms, the gas transforms into a mixture of freely moving charges. That mixture behaves differently from anything in everyday life. It becomes responsive to magnetic fields, capable of forming waves and filaments, and prone to glowing with a soft, luminous light. It is a matter that has slipped into a new kind of freedom. The sun is the most familiar example. Beneath its bright surface, plasma churns and rolls like a slow-motion ocean of fire. Yet, the movements are far more complex than any ocean on Earth. Charged particles drift through colossal magnetic fields, weaving patterns that stretch across the solar surface. These flows shape sunspots, guide solar flares, and drive loops of glowing material that arch gracefully from the sun's edge. From a distance, it may look chaotic, but within the motion is a sense of collective behavior, as if the particles are following quiet, unseen currents. The auroras near Earth's poles offer a gentler glimpse of plasma's beauty. When charged particles from the sun reach Earth, they follow the planet's magnetic field lines toward the poles. As they drift downward, they brush against the upper atmosphere, exciting atoms of oxygen and nitrogen. Those atoms then release their energy as light, creating rippling curtains of green, red, and violet. The movement looks almost alive, as though the sky were breathing glowing colors in slow, graceful waves. It is plasma interacting with our atmosphere, softened by distance and stretched across the night. Lightning is another reminder of plasma's presence much closer to home. A bolt forms when electrical charge builds inside a storm cloud until the air can no longer resist it. For a tiny fraction of a second, the air becomes so hot that electrons separate from their atoms, forming a channel of plasma. Through that channel, the stored electrical energy surges downward, illuminating the sky with a flash of white light. It is a fleeting form of plasma, born and extinguished so quickly that it almost feels unreal. Beyond our atmosphere, plasma fills space. Solar wind, a constant stream of charged particles flowing outward from the sun, moves through the solar system like a soft invisible tide. It brushes past planets, shapes comet tails, and influences the delicate magnetic bubbles surrounding certain moons and stars. Nebulae, the vast clouds of glowing gas scattered across the galaxy, are often made of plasma illuminated by the stars forming within them. Their colors, their shapes, and their soft glow all come from charged particles drifting through enormous stretches of space, interacting with starlight and magnetic fields. One of plasma's most intriguing qualities is its collective behavior. In a gas, particles mostly ignore one another, except during occasional collisions. In plasma, the story changes because the particles are electrically charged. They influence each other, even from afar. A shift in one region can send ripples through others. Fields and flows appear naturally, guiding the motion of millions of particles at once. It is as though the plasma becomes a single coordinated entity rather than a loose collection of individuals. Scientists often describe it as a fluid made not just of mass but of charge, responding to invisible lines of force that thread through the space around it. Magnetic fields play a large role in shaping plasma's behavior. When plasma moves through a magnetic field, it feels a gentle sideways push. This influences its flow, bending and twisting it into arcs, loops, and spirals. In the sun, enormous magnetic loops rise through the surface, carrying plasma with them. When those loops snap or reorganize, they release energy in events that can send particles across the solar system. Yet even in these powerful displays, there is a grace to the motion, a rhythm that feels more like a slow cosmic dance than the violence it truly represents. This sensitivity to magnetic fields is also what allows scientists on Earth to study plasma in controlled environments. Devices known as magnetic confinement machines use carefully shaped magnetic fields to hold plasma in place, preventing it from touching the surrounding walls. Even though the plasma inside these machines may reach temperatures hotter than the center of the sun, it never makes contact with the equipment because the magnetic field cradles it gently, keeping it suspended. This approach is part of the long, patient pursuit of fusion energy, an attempt to harness the same process that powers the stars. The plasma inside these machines hums softly with potential, a reminder that understanding this state could help unlock cleaner, steadier forms of energy in the future. Plasma glows so often because the separated electrons frequently collide with atoms and ions, giving them small bursts of energy. When these excited particles release that energy again, they emit light. The colors depend on which atoms are present and how much energy they receive. That is why auroras shimmer in greens and reds, why neon signs shine with warm orange tones, and why the sun radiates a bright white that carries the warmth of an entire star. Despite its presence all around the universe, plasma rarely appears in everyday life except in lightning, fluorescent lights, and a few man-made devices. Earth's surface is too cool and calm for plasma to form naturally for long periods. Yet, once you realize how common it is beyond our daily experience, the universe begins to feel different. Stars stop being distant points of light and become enormous spheres of ever-moving plasma. Nebulae stops being static clouds and becomes living structures shaped by magnetic fields and the quiet push and pull of charged particles. Plasma is the universe's most expressive state of matter, a form that thrives on heat, movement, and freedom. It is the state that carried the early universe through its first moments, the state that still fuels every star, and the state that paints streaks of color across the polar skies. As we drift further into the hidden faces of matter, plasma stands as the first reminder that once energy rises high enough, matter begins to unravel its familiar structure and reveal deeper behaviors. It invites us to look past the quiet surfaces of everyday life and imagine what forms matter takes under the brightest, hottest, most ancient conditions imaginable. The next journey we take is to the opposite extreme, where matter falls into a deep, silent order. When matter is warmed, it grows restless. Atoms jostle, molecules tumble, and the structure of everything becomes a little louder, a little more chaotic. But when matter is cooled slowly, steadily, deeply, the opposite happens. Motion softens, vibrations shrink. The frantic dance of particles becomes a kind of quiet meditation. And if the temperature falls far enough down toward the coldest limit nature allows, matter sometimes undergoes a transformation so strange and so elegant that it no longer behaves like any ordinary fluid. It becomes a superfluid, a form of matter capable of flowing without friction, without resistance, and without losing energy no matter how long it moves. Helium is the gateway into this peculiar world. Almost every substance found on Earth will freeze solid if cooled sufficiently. But helium refuses, even at temperatures where most materials become stiff and crystalline. Helium remains liquid, softly swirling, still able to flow. The reason is hidden in the quantum nature of helium atoms. They are light, nimble, and resistant to freezing, able to slip around one another even at temperatures near absolute zero. As the temperature drops closer to that unimaginable cold, something remarkable happens. The liquid helium undergoes a transition and becomes a superfluid, a substance with properties so unusual that it seems to defy the expectations of everyday physics. One of the most striking features of a superfluid is the absence of friction. In an ordinary liquid, motion eventually slows. A cup of water stirred with a spoon will swirl for a moment, then settle. The energy dissipates through countless tiny interactions between molecules, but a superfluid behaves differently. If you set it swirling, it simply continues. It glides without effort, slipping past itself and its surroundings with silk-like smoothness. In a perfectly quiet container, a superfluid could keep flowing endlessly, as though time had forgotten to nudge it back towards stillness. This frictionless nature leads to behavior that seems almost playful. A thin film of superfluid helium can climb the walls of its container, creeping upward like a liquid that has forgotten where gravity is supposed to apply. It can slide through microscopic pores and cracks that would stop any ordinary substance. If you place superfluid helium in a container with even the smallest imperfections, it finds them all and pours through them like a mist turned to liquid. It is as though the fluid refuses to be held back, choosing its own path with effortless grace. To understand why it behaves this way, it helps to imagine the particles inside the superfluid acting not as individuals, but as parts of a single unified wave. In most substances, each atom or molecule has its own motion, its own small patch of space, its own freedom, but in a superfluid, particles enter a state known as quantum coherence. They move as if they are one system rather than many separate pieces. Their behavior becomes coordinated, a shared motion that stretches across the entire fluid. You could draw a swirl into one corner of the superfluid, and the entire substance would recognize that motion instantly, responding as a unified whole instead of as countless independent particles. There is a quiet elegance to this idea. As the temperature falls and thermal noise retreats, the underlying order of quantum mechanics rises to the surface. What was once chaotic becomes synchronized. What was once a jumble of motions becomes a single flowing entity. In this sense, extreme cold does not simply slow things down. It allows hidden patterns to emerge. It reveals a kind of harmony that cannot be seen at higher temperatures, where motion is too wild for coherence to form. Many of the behaviors that define a superfluid stem from this shared motion. Eternal whirlpools, for example, are a direct consequence of it. In an ordinary fluid, swirling motion eventually breaks apart into smaller eddies, each one losing energy until the motion dissolves back into stillness. A superfluid refuses to do that. Its whirlpools are stable, long-lasting, and sharply defined. They can persist for extraordinarily long times because the fluid cannot dissipate the energy of rotation in the same way normal fluids do. Instead of decaying, the motion becomes quantized, meaning it can only exist at specific stable values. These whirlpools behave almost like delicate self-contained structures floating in the fluid in perfect equilibrium. Another strange behavior is the ability of superfluids to form incredibly thin films that spread across surfaces like an impossibly delicate coating. The film seems to move with a mind of its own, crawling over edges and creeping across boundaries until it covers everything it can reach. This movement is not driven by evaporation or pressure, but by the energy balance within the material itself. The superfluid seeks uniformity, so it spreads until its surface is as even as possible. Watching this process in the rare laboratories where it is visible can feel almost eerie, as though the liquid possesses a kind of silent curiosity. The most fascinating thing about superfluids is that they teach us something profound about the nature of order and motion. In our everyday world, extremes tend to create chaos. Heat leads to frantic movement, collisions, and disorder. But at the opposite end, where motion is nearly frozen out, something unexpected happens. Instead of settling into stillness, matter sometimes discovers new forms of organization. It aligns itself in ways that are invisible at warmer temperatures, choosing collective behavior over individuality. A superfluid is not simply a very cold liquid. It is a liquid that has revealed a deeper kind of unity. This unity demonstrates that the rules governing the tiniest particles can shape the behavior of entire substances. It is a reminder that quantum laws, which feel abstract and distant when applied to single particles or atoms, can sometimes rise into the macroscopic world. They can influence something as large as a swirl in a container or the creeping of a film up a wall. It is a bridge between two worlds that normally feel far apart. The strange world of the very small and the familiar world of the very large. The discovery of superfluidity in helium provided one of the earliest demonstrations that quantum mechanics does not belong solely to the realm of tiny particles and exotic mathematics. It also shapes the everyday behavior of certain materials when conditions are just right. That connection has inspired decades of research into other forms of quantum coherent matter, from superconductors to exotic states found inside stars. Each one reveals a little more about how matter organizes itself when the usual thermal noise is stripped away. Superfluids are more than a curious footnote in physics. They are a gateway into a deeper understanding of how nature behaves when it is pushed toward its limits. They show that beneath the surface of the world we know is a landscape of hidden order, waiting for the right conditions to emerge. And they remind us that even in a universe filled with motion, noise, and change, there are places where matter chooses to move in perfect harmony. Our next state pushes this idea of quantum harmony even further, creating a single entity from a vast collection of individual atoms. In the warm world of everyday experience, atoms behave like countless individual dancers moving across a crowded floor. Each one has its own rhythm, its own tiny patch of space, its own energy and motion. They drift, bump, and vibrate in constant independent activity. But as these atoms are cooled slowly, steadily, carefully, a change begins. Their movements soften, their individuality fades, the frenetic jostling that defines warmer temperatures quiets into a calmer, more coordinated sway. And if the cooling continues far enough, down to temperatures startlingly close to absolute zero, matter can fall into one of the most extraordinary states ever discovered. It becomes a Bose-Einstein condensate, a state where trillions of atoms stop behaving as separate entities and begin acting as one unified wave. To understand why this happens, it helps to imagine atoms not as tiny rigid spheres, but as gentle ripples in a field, each one spreading out into space. In normal conditions, these ripples are so small and energetic that they barely overlap. Each one is distinct, a little blur of probability that remains confined to its own microscopic territory. But as atoms cool, their energy shrinks, their ripples broaden. Their wave-like nature, usually invisible in daily life, begins to stretch outward. When the temperature becomes extremely low, these waves grow so large that they begin to overlap significantly. Instead of behaving like separate ripples, they merge, eventually forming one broad unified wave. At that moment, the atoms inside the cloud fall into a shared quantum state. Imagine a choir in which every singer is improvising their own melody. The result is lively but chaotic. Now imagine the choir softening its voices, slowing its rhythm, and eventually finding a single note that everyone can sing together, perfectly aligned, perfectly steady. That is what the atoms experience as they form a Bose-Einstein condensate. The chaotic noise of individual motion quiets into a harmonious unity. The entire collection behaves as one entity, as if all the atoms were sharing a single identity. Their positions, their motions, their properties become linked, no longer distinct and no longer independent. Two physicists working decades apart predicted this transformation in the early 20th century and separated by continents. Their prediction suggested that if a cloud of certain atoms were cooled close enough to absolute zero, their wave-like behavior would dominate, and the atoms would condense into a single quantum state. For years, it remained a theoretical curiosity. The technology to cool atoms to such low temperatures did not yet exist, but as cooling techniques improved over the decades, researchers gradually approached the threshold needed to see this phenomenon. Finally, in the 1990s, atoms were cooled to the necessary temperature, and the first Bose-Einstein condensate was created in a laboratory. For the first time, scientists watched matter slip into unified motion. One of the most fascinating properties of a Bose-Einstein condensate is how visible its quantum nature becomes. Normally, quantum behavior is hidden behind the noise of everyday motion. At room temperature, atoms rattle around too quickly for their wave-like nature to show itself clearly. But in a condensate, the motion is so slow, so coordinated, that the underlying quantum structure rises into full view. Experiments that would be impossible or invisible at warmer temperatures become gentle demonstrations of quantum physics, acting on a scale you can see. Researchers can nudge the condensate and watch waves travel across it like ripples across a perfectly calm pond. They can confine it in magnetic or optical traps, creating shapes that hold steady as though the matter were molded into place. They can split it into two parts and recombine them again, observing interference patterns that reveal its unified nature. These interference patterns are one of the clearest signs that condensates act as a single entity. When the separate pieces overlap, their waves reinforce or cancel in specific patterns, much like overlapping ripples on water. But here the ripples are made of matter itself. Among the most poetic experiments ever performed with a Bose-Einstein condensate involves slowing down light. Under normal conditions, light moves at tremendous speed, crossing vast distances in small fractions of a second. But when a pulse of light is sent through a Bose-Einstein condensate, something remarkable happens. The atom's coordinated motion creates an environment where the light interacts strongly with the material, losing speed as it travels. In some experiments, researchers have slowed light to the pace of a gentle stroll. In others, they have stopped it entirely, holding the information within the pulse before releasing it again. Such work shows how unusual the condensate structure is, a place where motion slows so much that even light, the universe's fastest traveler, must pause. The idea of atoms acting as one might sound abstract, but it creates very real, very visual behaviors. When a Bose-Einstein condensate is allowed to expand after being released from a trap, it spreads in a smooth, coordinated way, almost as though it were a single soft object rather than countless individual particles. If two condensates are brought together, they do not mix like ordinary fluids. Instead, they produce elegant interference patterns, stripes or ripples that reveal the underlying, wave nature of the matter. These patterns look almost like the marks left by gentle brushes of wind across sand. The unity of the condensate also explains why its behavior can feel so serene. In most materials, particles collide, exchange energy, and reorganize in constant messy motion. In a Bose-Einstein condensate, these interactions become part of a shared pattern. Motion does not dissipate in the usual way. It becomes part of the system's overall flow. The result is motion that feels almost intentional, as if the matter were moving with a single integrated purpose. It is quiet, slow, and astonishingly coordinated. When you step back and look at the broader picture, a Bose-Einstein condensate teaches something profound about nature. At high temperatures, matter hides its deeper structure beneath noise and chaos. Every particle behaves independently. Every vibration is a separate voice. But at extremely low temperatures, when energy is drained away and motion becomes soft, unity emerges. The particles give up their individuality, choosing instead to act together as one. It is a reminder that extreme cold can be as revealing as extreme heat. Just as rising temperatures unveil states like plasma, falling temperatures unveil states where order and harmony take center stage. This state also reinforces the idea that quantum mechanics is not a distant set of rules confined to tiny particles or exotic materials. It shapes the behavior of real matter under the right conditions. Quantum rules are always present, woven into the fabric of reality. Even if they're usually drowned out by everyday motion, a Bose-Einstein condensate brings those hidden rules into the open, placing them on a stage where they can be seen directly, not just inferred or calculated. The unity at the heart of the condensate makes it one of the most beautiful states of matter. It shows that when the noise of thermal motion is quieted and the particles lose their separate rhythms, matter can perform in perfect harmony. What begins as a cloud of individuals becomes a single graceful wave. What begins as chaos becomes coherence. And what begins as ordinary atoms becomes a window into the deeper patterns that shape everything at the most fundamental level. As you move through this journey of hidden states, the Bose-Einstein condensate stands as a gentle reminder that even in a universe filled with constant motion, there exists places where matter pauses, aligns, and whispers in one voice. This soft coherence is essential to the next state we explore, one where electrons find a similar unity to move with perfect efficiency. Electricity feels effortless when you flick on a light or plug in a device. But beneath that simple motion is a hidden struggle. In ordinary materials, electrons cannot move freely without bumping, jostling, and scattering their way through a tangled forest of atoms. Every little collision steals a bit of energy, turning part of the electrical current into heat. This is why wires warm up, why devices lose efficiency, and why electricity always comes with a quiet cost. But when certain materials are cooled far enough, something almost magical happens. The resistance that normally slows electrons disappears entirely, and electrical current begins to move with perfect, unhindered grace. This is the world of superconductors, a state of matter where electricity flows as smoothly as a whisper glides through still air. At the heart of this transformation is a subtle shift in how electrons behave at very low temperatures. In everyday conditions, electrons move independently, each following their own path through the material. Their freedom is limited by imperfections in structure, vibrations of atoms, and interactions with other electrons. But as the temperature falls, those atomic vibrations quieten, the chaos fades, and in that calm, electrons begin to behave differently. Instead of acting as individual particles, they pair up into gentle coordinated partnerships known as Cooper pairs. These pairs are incredibly delicate, but they share an important property: they move through the material in synchronicity. This pairing allows electrons to glide smoothly past obstacles that would normally deflect or scatter them. It is as though the material transforms into a wide, perfectly polished corridor. Instead of being buffeted around by imperfections, the Cooper pairs slip through without friction, like dancers gliding across a floor without ever catching a toe. The result is extraordinary. Electrical resistance drops not partially, not gradually, but all the way to zero. Once a current begins to flow in a superconductor, it can move endlessly without losing energy. If a loop of superconducting wire is set into motion, it will keep circulating its current for as long as the material stays below its critical temperature, without fading, without dimming, and without needing any additional push. This behavior may sound abstract, but its effects can be seen in one of the most striking demonstrations in physics: magnetic levitation. When a superconductor is cooled below its transition temperature and placed above a magnetic field, a surprising thing happens. It locks itself into position, hovering stably above the magnet. It does not wobble, it does not slide, it simply floats. This levitation comes from a subtle dance between the magnetic field and the superconducting state. As the electrons pair up and circulate without resistance, they create currents that push back against the magnetic field, effectively freezing it into a fixed pattern. The superconductor becomes a quiet anchor point, allowing the object to hover as though held in place by invisible strings. Watching a small disk of superconducting material lift itself above a magnet and rest there, supported only by the delicate balance of quantum behavior, feels almost dreamlike. The motion is silent and smooth, giving the impression that gravity has been politely asked to step aside for a moment. Even more impressively, if the magnet or the superconductor is moved, the suspended object glides along with it, maintaining its distance and orientation. It is an elegant reminder that superconductivity is not just a theoretical curiosity. It produces effects that are visible, tangible, and deeply enchanting. But the story of superconductivity reaches far beyond levitation. The ability to carry current without loss could transform how society uses energy. Long-distance power transmission could become vastly more efficient, reducing the waste that occurs as heat in ordinary wires. Powerful electromagnets used in medical imaging or scientific research could operate with far less energy. Particle accelerators, fusion experiments, and even transport systems such as magnetic levitation trains could all run more smoothly and more efficiently. The challenge, of course, is that most known superconductors only function at extremely low temperatures, often requiring cooling with liquid helium. These conditions make practical applications expensive and complex. This is why finding room temperature superconductivity has captivated scientists for decades. If a material could become superconducting at temperatures closer to those we experience daily, it would revolutionize almost every aspect of modern technology. Over the years, researchers have discovered materials that become superconducting at higher and higher temperatures, some even functioning when cooled with liquid nitrogen rather than the far colder liquid helium. Each discovery edges closer to the long-sought goal. Recently, several promising candidates have been found under extremely high pressures, suggesting that nature may hold the key, but only reveals it under the most intense conditions. Achieving superconductivity at everyday pressures and temperatures remains a scientific frontier, one marked by careful experiments, surprising breakthroughs, and the occasional false start. At its core, superconductivity is a state where matter behaves as though all the electrons have agreed to cooperate. Instead of scattering and colliding, they glide together in perfect synchrony, forming a single unified flow. It is like watching a flock of birds in the sky. When they move independently, the motion appears scattered, but when they align and turn in unison, their movement becomes mesmerizing, fluid, and efficient. Superconductivity is the electronic equivalent of that harmony. The paired electrons follow a shared rhythm, shaping their motion into a collective dance that loses no energy along the way. This harmony also explains why superconductivity disappears when the material becomes too warm. Heat introduces disorder, shaking the atoms and disrupting the delicate partnerships between electrons. Once the motion becomes too chaotic, the pairs break apart. Resistance returns, and the superconductor becomes ordinary again. Only when the temperature is low enough for calm to settle over the atoms can the coordinated motion reappear. In this way, superconductors remind us that quiet conditions are sometimes the key to revealing hidden order. When you step back and view the full picture, superconductors feel like nature's way of showing what happens when motion becomes perfectly organized. They are a glimpse into a world where energy does not trickle away, where motion does not fade, and where behavior that seems impossible in daily life becomes the natural state of things under the right conditions. They highlight the deep connection between quantum mechanics and the macroscopic world, revealing that when matter is cooled enough to soften the background noise, new behaviors begin to rise gently into view. Superconductors are not just another chapter in the hidden state story, they are a link between the quantum world's subtle rules and the larger world we can see, touch, and study directly. They stand as a reminder that beneath the familiar patterns of everyday materials lies a landscape of astonishing possibilities, waiting patiently for the right conditions to reveal themselves. Our journey now shifts slightly, leaving the extremes of deep cold for a gentle territory where order and flow meet in perfect balance. There's a quiet elegance in the way nature handles the space between extremes. It rarely leaps abruptly from one state to another. Instead, it lingers in the middle, pausing in places where order and motion share the same room. Liquid crystals are one of the clearest examples of this gentle in-between world, a state of matter that carries just enough structure to hold shape and just enough looseness to flow. They behave like liquids with a sense of direction, or solids softened into motion, creating patterns and behaviors that are unlike anything else in the familiar world. If you look at a simple liquid, its molecules drift around with no preferred orientation. They tumble, roll, and slide unpredictably, forming a constantly shifting arrangement that has no long-range order. A solid, by contrast, locks its molecules into fixed positions and orientations, creating repeating patterns that persist throughout the material. Liquid crystals sit exactly between these behaviors. Their molecules tend to point in similar directions, forming a kind of orientational order, yet they are still free to move past one another, flowing just like an ordinary liquid. This partial alignment gives liquid crystals their shimmering, shifting appearance. Light interacts with the structured orientation in unusual ways, bending, twisting, and scattering differently depending on how the molecules are arranged at that moment. This molecular alignment can be imagined like a group of people roaming a room. In a solid, everyone stands in a neat grid, perfectly arranged and unmoving. In a typical liquid, everyone faces random directions, drifting without a plan. But in a liquid crystal, everyone still moves, but in a loosely coordinated fashion, facing roughly the same direction as they wander. That shared orientation influences how the group behaves as a whole. Paths open and close, patterns ripple across the crowd, and subtle waves of motion pass through the system. As people turn and adjust, the molecules of a liquid crystal do something similar, creating a fluid that flows with a hint of structure. The beauty of liquid crystals becomes especially visible when temperature or pressure changes their degree of alignment. A slight increase in heat can cause molecules to tilt differently, forming new layers or patterns. As they shift, the way they interact with light changes, producing iridescent colors or soft textures that shimmer when the material is rotated. These patterns often appear in soap films, insect wings, and oil slicks on water, where the delicate balance between order and motion leads to natural displays of color. Each subtle variation in molecular orientation creates a slightly different interaction with light, painting the surface with gentle blues, greens, and violets. Liquid crystals also display phases of their own, each reflecting a different level of organization. In some phases, the molecules align in a single direction but remain free to move. In others, they form layered structures, sliding past each other like sheets of paper. Certain phases create twisting arrangements, forming helical patterns that interact with light in spirals. These forms can transition from one to another simply by adjusting the temperature by a small amount. A material may appear cloudy one moment, then suddenly clear or colorful the next, as the molecules rearrange themselves into a more or less ordered pattern. This responsiveness is one of the reasons liquid crystals are so useful and so fascinating. They are materials that shift easily, smoothly, and predictably between different degrees of order. Nature makes generous use of liquid crystal behavior, especially in biological systems. Cell membranes, for instance, are built from molecules that behave like liquid crystals. They're aligned enough to create a stable barrier around the cell, but fluid enough to allow proteins and signals to drift across their surface. This balance between order and mobility is essential for life. It allows cells to maintain a shape and structure while being dynamic and responsive. Without this liquid crystalline behavior, processes such as signaling, nutrient transport, and membrane reshaping would be far less efficient. The same principle appears in fibers such as collagen, where molecules align into long structured arrangements that provide strength, yet retain enough flexibility for tissues to bend and stretch. Even the arrangement of DNA inside cells carries hints of liquid crystalline order during certain stages of organization. Wherever nature needs a material that can hold form while still adapting to its environment, liquid crystalline phases appear naturally, as though the universe has learned that the middle ground often offers the best of both worlds. Humans have learned to use this unusual state of matter in their own technologies, particularly in the screens we use every day. The pixels in many displays rely on liquid crystals that can twist or align in response to small electrical signals. As molecules rotate, they change the way light passes through them. Layer upon layer of liquid crystal cells sit behind each pixel, shifting their orientation to either allow light through or block it. The transitions are small, precise, and incredibly fast, allowing entire images to form from millions of tiny controlled adjustments. Every soft glow from a digital clock, every color on a flat screen, every gentle fade on a modern display is made possible by the behavior of liquid crystals. Despite their technological importance, the true charm of liquid crystals lies in their quiet refusal to be classified as simply one thing or another. They live in the gentle territory between perfect order and complete freedom, taking elements from both and combining them into something new. They show that matter does not have to commit fully to being a solid or a liquid. It can pause in that middle ground, forming textures and patterns that neither extreme can produce alone. This fondness for in-between states seems to be a recurring theme in nature. From the foam on ocean waves to the soft gel inside cells, the materials around us often prefer partial organization over rigid categories. The world is filled with gradients, blends, and transitions. Liquid crystals are part of that broader story, a reminder that the most interesting behaviors often emerge not at the extremes, but in the quiet spaces between them. As you imagine these aligned yet flowing molecules shifting gently with temperature, forming rippling colors and delicate structures, it becomes clear that liquid crystals are less a curiosity and more a testament to nature's creativity. They show that matter is capable of balancing order and movement so gracefully that it becomes something entirely its own. And in that balance we find a new way to see the world, not as a place of strict categories, but as one shaped by subtlety, nuance, and quiet transitions that cause beauty. Now we turn to a different kind of stability, one built not on orderly repetition, but on beautiful, lasting disorder. When you picture a solid, It is easy to imagine a material built from perfect repetition, a quiet, orderly arrangement of atoms stacked neatly like bricks in an invisible wall. Many solids truly are like this. Their atoms lock into repeating patterns that stretch across the material in all directions, creating a structure so regular that you could predict where each atom sits just by knowing the pattern. But not every solid obeys this elegant architecture. Some form in a hurry, or cool too quickly, or settle in ways that prevent the atoms from finding a comfortable repeating arrangement. These are amorphous solids, materials whose internal structure is not neatly crystalline, yet who still hold their shape with as much persistence as their more orderly relatives. They're a reminder that disorder can be just as durable as order, and sometimes far more interesting. Glass is the most familiar example. When you look through a window, you are peering through a solid whose atoms are arranged not in tidy rows, but in a tangled, irregular network. During the cooling process, the atoms become trapped before they can find positions that form a repeating pattern. The result is a structure that resembles a frozen liquid, as though the material were caught mid-motion and held in place. Obsidian, the volcanic glass forged in cooling lava heat, behaves similarly. Its atoms rush into place so quickly that they cannot organize themselves in time, locking it into a hardened but disordered form. Both materials feel solid to the touch and behave like traditional solids, but inside there is no long-range order, only local pockets of organization surrounded by a larger web of randomness. This lack of structure often leads to a common myth whispered through time, that glass flows slowly under its own weight, thickening at the bottom of old windows and thinning at the top. It is a charming idea, the image of a window pane very gradually sagging over centuries. But modern research shows that this myth arises from the way early glass was made, not from the glass flowing over time. Historical panes were uneven when they were created, and builders often placed the thicker edge at the bottom for stability. In reality, glass at room temperature is effectively rigid. With no measurable flow on human timescales, if it does move at all, the process would take far longer than the age of the universe. The disorder within glass does not weaken it or cause it to melt slowly downward. It simply gives it a different kind of stability, one that is not built on repeating patterns but on the tight, irregular connections between atoms. This disordered structure also influences how amorphous solids interact with light. In crystals, the regular arrangement of atoms produces predictable optical behaviors. Light waves travel through them in orderly paths, sometimes splitting or bending in ways that reflect the material's underlying symmetry. But in amorphous solids, the irregular arrangement scatters light differently. Glass is transparent not because of its disorder, but because its atomic structure does not disrupt the passage of visible wavelengths. Light passes without being absorbed or scattered by the atomic network. This delicate balance between transparency and strength is the reason glass makes such a versatile material for windows, lenses, and countless other uses, all while retaining its identity as a solid built from disorder. In other amorphous solids, this irregular structure creates different effects. Obsidian, for example, has a natural sheen and sharpness that arise from the way light interacts with its non-crystalline arrangement. It can fracture into cuts so smooth and precise that ancient cultures used obsidian blades for surgical purposes, appreciating their sharpness long before stainless steel existed. The lack of long-range order allows the edges to cleave into incredibly fine points. Even polymers, which can behave as amorphous solids under certain conditions, owe some of their unique optical and mechanical properties to their tangled molecular arrangements. A concept called structural frustration helps explain why some materials become amorphous. Atoms often have preferred ways of organizing themselves. They might naturally form tetrahedra or octahedra or create repeating layers that minimize their energy. But sometimes the preferred structures cannot tile space perfectly. Imagine trying to fit triangles of different sizes into a perfect mosaic without any gaps. No matter how carefully you arrange them, there will always be empty spaces or overlapping edges. In the same way, Atoms in certain materials cannot arrange themselves into a repeating pattern that satisfies all of their preferred interactions. They become trapped in a state where local order exists, small clusters that appear structured, but that order cannot extend throughout the material. These pockets of local structure create a material that feels solid and behaves predictably, even though its overall pattern is irregular. This frustration is not a flaw. It is a reminder that nature often settles into stable configurations that do not look orderly in the traditional sense. The atoms may want to organize fully, but the geometry of their preferences prevents it. Instead, they find a different kind of equilibrium, one that is disordered on the large scale, but structured enough on the small scale to hold together firmly. When viewed from another angle, disorder can be seen as its own type of order, a kind of stability born from randomness rather than repetition. In amorphous solids, the positions of atoms may not follow a neat blueprint, but they settle into an arrangement that resists movement, deformation, and melting just as effectively as a crystal lattice. Each atom becomes locked into place by its neighbors, forming a dense, interwoven network that does not require symmetry to function. It is a little like a crowd packed tightly enough that nobody can move freely even without a planned arrangement. The overall structure becomes rigid and supportive. Reflecting on amorphous solids reveals something meaningful about the diversity of matter. Not everything that is stable must be orderly. Not everything that is strong must be beautifully aligned. The universe has room for materials that are messy, irregular, and unpredictable in their inner architecture while still being reliable, durable, and visually striking. These solids remind us that nature is not limited to one style of organization. It is just as comfortable creating disorder as it is assembling perfect lattices. When you look through a pane of glass, hold a piece of obsidian, or see the glossy shine of a polymer, you are encountering this quiet category of solids that refuse to be boxed into crystalline patterns. They hold shape through a dense web of atomic connections rather than through repeating structures. And in that refusal to follow tradition, they offer a small lesson. Sometimes things can be strong, clear, and stable, not because they are perfectly organized, but because they have found balance in the beauty of disorder. Our next quiet exploration takes us deeper into the soft materials that embrace fluidity and structure simultaneously, living perpetually in the middle ground. Soft matter sits in a world of its own, occupying the landscape between solids and liquids with an ease that feels almost intuitive once you notice it. These materials appear everywhere in daily life, in kitchens, in nature, inside our own bodies. Yet, they behave in ways that don't quite fit the familiar categories. They can be squishy but structured, flowing yet firm, delicate but surprisingly resilient. They are the quiet middle ground of matter, revealing that the universe is just as comfortable creating things that blur boundaries as it is creating things that fit neatly into them. Gels are one of the gentlest examples of this in-between world. At first glance, a gel can look like a solid. It holds its shape, sits calmly on a surface, and doesn't spread out like a liquid would. But look closely and you notice something strange. Press lightly on a gel and it gives way. Stir it and it trembles. Spread it and it yields. Gels are made from liquids trapped inside delicate networks of molecules, something like a liquid held in a loose, flexible cage. The network forms a three-dimensional structure, and the liquid fills every gap within it. This means gels are mostly liquid by content, but mostly solid by behavior. They do not flow freely, yet they're far from rigid. Nature makes extravagant use of gels. The gel-like environment inside your cells, known as the cytoplasm, is one of the most important substances in biology. It holds enzymes, nutrients, and organelles in place while still allowing them to drift and interact. The consistency is neither watery nor stiff. It is balanced, a living medium where processes can unfold without everything sinking to the bottom or floating away. Even your eyes rely on gels. The vitreous humor that fills each eye is a transparent gel that maintains the eye's shape while allowing light to pass through undisturbed. Without this clear jelly-like substance, vision would be distorted or impossible. Foams sit in another part of the soft matter landscape. They're made not of liquid supporting liquid, but of gas wrapped in thin films. When gas bubbles are trapped inside a liquid, they create a structure that is surprisingly stable. A spoonful of whipped cream, a bubble bath, a rising loaf of bread, the soft head on a freshly poured root beer. All of these are foams. Their structure depends on the delicate film surrounding each bubble. These films are flexible and constantly adjusting, bending and stretching in response to pressure. Foam can be squeezed, reshaped and compressed because gas is easily displaced. But the thin liquid films hold the overall structure together. Foams show how matter can take on shapes that are neither smooth nor rigid, but something entirely different. Their behavior depends on the balance between surface tension, pressure, and the liquid making up the films. For example, shaving cream feels surprisingly solid, yet it remains airy and light because the bubble network maintains its shape. Sea foam forms when waves churn organic material into bubbles, creating delicate layers that drift along the shore like a temporary landscape sculpted by wind and water. These materials behave nothing like ordinary liquids or solids, yet they remain stable long enough for us to recognize their form. Colloids add another dimension to the story. These are mixtures where tiny particles are suspended evenly throughout a fluid. Milk is a colloid, with fat droplets dispersed inside water. Mist is a colloid of tiny liquid droplets suspended in air. Paint is a colloid made from pigment particles held in a liquid medium. These particles are small enough to remain suspended indefinitely due to random motion, yet large enough to scatter light in ways that give the mixture its appearance. This is why milk looks white and cloudy, why fog glows softly when light hits it, and why certain paints shimmer or appear opaque. Because colloidal particles do not settle easily, colloids behave differently from simple mixtures or solutions. They can be surprisingly stable, resisting separation even when left undisturbed for long periods. That stability is a key reason why biological fluids work the way they do. Blood, for example, is a colloid containing red blood cells and proteins suspended in plasma. The particles remain mobile, allowing nutrients and oxygen to travel smoothly through the body. Many bodily fluids rely on colloidal behavior to maintain viscosity, dispersal, and consistency, making colloids essential to life as we know it. What makes soft matter particularly fascinating is the way it blends behaviors typically associated with different categories. Gels resist flow like solids but move under pressure like liquids. Foams can be sculpted like solids but collapse like liquids when disturbed. Colloids spread smoothly like liquids but scatter light and hold form like more structured materials. Across all these examples, the key features are flexibility, responsiveness, and a kind of dynamic stability that stands apart from the rigidity of crystals and the looseness of typical fluids. The reason soft matter behaves so differently lies in energy scales. The forces holding these materials together are weak compared to the forces holding atoms in a crystal. Thermal motions, the subtle vibrations caused by temperature, are strong enough to influence the structure directly. Where a solid resists rearrangement because its atoms are tightly bound, soft matter responds gently to changes in temperature or pressure. Gels soften, foams collapse or grow stronger, and colloids thicken or thin depending on how their components interact. The fine balance of forces makes soft matter extremely sensitive, which is why small changes in conditions can produce large effects. This sensitivity gives soft matter an unusual place in the natural world. It allows forms that are adaptable rather than fixed, structures that respond rather than resist. Many biological systems rely on this exact balance. Cell membranes, thin layers of amphiphilic molecules, behave like two-dimensional liquids that hold their shape while allowing proteins to drift through them. Cartilage behaves like a gel, cushioning joints by redistributing water within its structure. The extracellular matrix, which supports tissues throughout the body, behaves like a blend of gels and colloids, providing strength and flexibility at the same time. Soft matter also plays a central role in food textures, cosmetics, medical materials, and countless household items. Yogurt, mayonnaise, hand lotion, toothpaste, gelatin, shaving cream, marshmallows, and even wet sand rely on colloidal, gel-like, or foam-like structures. Their consistency affects how they spread, how they feel, and how they respond when touched or pressed. Each material occupies a unique place in the soft matter spectrum, where flow and structure meet. What makes gels, foams, and colloids so captivating is that they embody nature's fondness for the middle ground. Instead of choosing rigidity or fluidity, they blend the two, creating materials that are stable but sensitive, structured but adaptable. They demonstrate that matter does not need to fall sharply into a single category to behave beautifully or function effectively. Some of the most useful and interesting materials in the world exist precisely because they blur these lines. In soft matter, boundaries fade, categories loosen, and the true creativity of the physical world becomes clear. We now examine a material that perfects this balance of structure and flow in the form of incredibly long, flexible chains. Polymers are among the world's quietest materials. You encounter them constantly in clothing, in food, in nature, in your own body. Yet, their behavior often feels mysterious until you look closely at what they truly are. At their core, polymers are long chains made from repeating molecular building blocks linked together one after another like beads on a necklace. But unlike a neat, well-behaved necklace that lies flat and tidy, polymer chains twist, coil, bend, knot, stretch, and tangle into shapes that shift with temperature, pressure, and time. Their behavior sits in the comfortable territory between rigidity and softness, giving rise to materials that can be stretchy, strong, springy, stiff, silky, or almost fluid, depending on how the chains interact. Imagine each polymer chain as a length of flexible spaghetti so thin you could never see it, wriggling invisibly among countless others. These chains are not straight. They curl and loop in unpredictable directions. Sometimes they drape loosely, forming wide coils that move gently with small amounts of force. Sometimes they knot themselves into dense tangles, creating a structure that resists stretching until the force becomes large enough to pull the knots apart. When millions of these chains occupy the same space, their collective behavior shapes the material they form. One of the defining features of polymers is that their chains can both stretch and recoil. When you pull on a polymer, the chains straighten out, extending like tiny springs. When you release the tension, they snap back toward their coiled shapes, restoring the material. This is why rubber bands stretch so far without breaking, why certain fibers can be pulled taut and then return to their original length, and why elastic materials feel so responsive under your fingers. The chains resist being fully straightened because they prefer the coiled, entropic comfort of their tangled arrangement. They behave like countless microscopic springs, blending together into one continuous elastic response. This entanglement is not just a charming image, it creates real mechanical effects. When polymer chains are very long, they weave around each other like threads in a loose fabric. These interconnections prevent the chains from sliding past one another easily, which gives the material strength. But the entanglement is not permanent. Over long periods, especially at warmer temperatures, the chains can slowly slither and reconfigure themselves, allowing the material to change shape. This is why some polymers behave like solids when stressed quickly, but like thick liquids when left alone long enough. This behavior is called viscoelasticity, a blend of viscosity and elasticity, showing that polymers can resist deformation like a solid in one moment and flow like a liquid in another. A simple example is a blob of silicone putty. Tap it sharply and it feels firm, bouncing in a way that suggests strength. But leave it on a tabletop for a few minutes and it slowly spreads out, flowing like honey. The same material responds differently depending on the timescale. On short timescales, the chains do not have time to disentangle, so the material acts stiff. Over longer timescales, the chains gradually rearrange, allowing the material to flow. Many natural and synthetic polymers behave this way, revealing that time is an ingredient in their mechanical character, just as much as temperature or chemical composition. Nature has been crafting polymers far longer than humans have. Silk, for example, is a marvel of natural polymer engineering, the chains of proteins that make silk twist and align into strong, lightweight fibers that resist snapping while still remaining soft to the touch. Spider silk, in particular, combines high tensile strength with surprising flexibility, all thanks to the arrangement of its protein chains. Rubber from plants behaves differently, but for similar reasons. Its polymer chains can stretch drastically before pulling back, giving natural rubber its smooth elasticity. Cellulose, the polymer that makes up the structure of plants, forms long, sturdy chains that bundle together into fibers. These fibers create rigidity for tree trunks, stems, and leaves, allowing plants to reach upward while remaining stable. The mechanical properties of wood, cotton, and paper all originate from these chains interacting, bundling, and reinforcing one another. Then there is DNA, perhaps the most extraordinary polymer known. It consists of repeating units arranged into two intertwined chains that store genetic information. The way DNA coils, bends, and folds determines how cells function and replicate. Proteins, too, are polymers whose behavior depends entirely on the way their chains fold into specific shapes. Every enzyme, every structural filament inside a cell, every molecular motor that keeps life running is built from polymer chains that have learned to twist into purposeful forms. Humans have created their own polymers as well, taking inspiration from natural structures. Plastics, nylons, and synthetic elastomers are built from chains designed to create specific behaviors. Some plastics are rigid, formed from polymers that are tightly packed and heavily entangled. Others are flexible with chains that slide more easily past one another. The softness of a plastic bag, the rigidity of a ruler, the toughness of a football helmet, and the springiness of a foam cushion all emerge from the length, arrangement, and entanglement of polymer chains. The temperature of a polymer greatly influences its behavior. When cold, the chains stiffen and lose flexibility. A stretchy plastic may become brittle on a freezing morning because the chains cannot slip past each other easily. When warm, the chains gain mobility, making the same material softer or more malleable. Some polymers have a glass transition temperature, a point where they shift dramatically from being brittle and glass-like to being rubbery and flexible. This transition shows how closely the behavior of polymers is tied to the energy in their environment. Chain length also plays a profound role. Short chains create materials that can flow or melt easily because the chains do not tangle enough to resist motion. Long chains become knotted together, creating dense webs that lead to toughness and elasticity. The degree of entanglement determines how quickly the material responds to force, how it deforms, and how it recovers. A material with lightly entangled chains may flow rapidly under pressure, while one with heavily entangled chains may barely move at all. Even the presence of crosslinks, small chemical bonds that tie one chain to another, can transform the behavior of a polymer. A lightly cross-linked material may stretch and relax easily. A heavily cross-linked material, such as the rubber used in car tires, becomes stiff, resilient, and able to withstand repeated stress without deforming permanently. The diversity of polymer structures explains why this class of materials is so incredibly versatile. Life depends on polymer chemistry at every scale. The structures of cells, the networks that give tissue shape, the fibers that hold muscles together, the protein machinery that catalyzes reactions and repairs damage, and the genetic information that guides development all rely on chains capable of folding, stretching, and interacting. Without polymers, biological systems would lose flexibility, adaptability, and the ability to store information. They are the quiet foundation of life's complexity. When you zoom out, polymers feel like a bridge between softness and strength, between order and flexibility. They are neither rigid like a crystal nor free-flowing like a liquid. Instead, they occupy a space where shape and motion coexist. Their tangled chains create materials that can respond, adapt, and persist in ways that no simple solid or liquid could manage. And because their behavior depends so closely on temperature, structure, and entanglement, polymers reveal just how much the properties of matter arise from the hidden architecture within. Whether you're holding a silk scarf, stretching a rubber band, typing on a plastic keyboard, or even reading the genetic code inside your own cells, you are interacting with polymer chains shaped by countless loops, twists, and turns. These materials show that strength does not have to mean rigidity, and that flexibility does not require weakness. In the world of polymers, structure and motion weave together. creating some of the most versatile and essential materials ever discovered. Our journey now takes us from these delicate chains to the immense high-pressure environments at the heart of giant planets. Deep inside the largest planets in our solar system, far beneath the swirling clouds and colorful storms, matter enters a state that cannot be found naturally anywhere on Earth. It exists only where pressure becomes almost unimaginable, where the weight of tens of thousands of kilometers of atmosphere presses downward with unimaginable force. In those hidden depths, hydrogen, the simplest and most abundant element in the universe, transforms into something spectacular. It becomes metallic hydrogen, a shimmering, electrically conductive state that behaves more like a gleaming molten metal than the gentle gas we know at the surface. This rare form of matter sits at the hearts of Jupiter and Saturn, shaping their magnetic fields, their structure, and perhaps even the story of their formation. To appreciate how unusual metallic hydrogen is, it helps to start with hydrogen as we normally experience it. Under ordinary conditions, hydrogen forms small pairs with two atoms joining into simple molecules. These molecules drift freely as a gas, barely interacting, light enough to float upward through air. Even when cooled into a liquid or frozen into a solid, the molecules stay bonded together in soft, almost delicate clusters. Nothing about everyday hydrogen hints at the metal it can become under the right conditions, but the interiors of giant planets are anything but ordinary. Deep inside Jupiter, the pressure climbs rapidly as you travel downward. A layer of molecular hydrogen sits on top, behaving much as you might expect, but as the pressure increases, the molecules begin rearranging. At pressures millions of times greater than those at Earth's surface, hydrogen molecules are squeezed so tightly that their electrons can no longer remain bound to individual atoms. The electrons begin to roam freely, forming a sea of charge that can move through the material with ease. This is the hallmark of metal. Electrons drift together, gliding through the substance in smooth currents that allow it to conduct electricity extremely well. This transformation creates a state of hydrogen that is unlike any other. Instead of a transparent gas, it becomes reflective and shiny. Instead of insulating, it becomes conductive. Instead of behaving like a soft molecular fluid, it behaves like a dense metallic liquid. It is thought that this metallic layer may extend for tens of thousands of kilometers inside Jupiter, forming a vast ocean of shimmering conductive hydrogen. Although we cannot see it directly, computer models and experiments suggest that it behaves somewhat like Mercury, dense, fluid, and electrically active. This electrical activity is one of the most important features of metallic hydrogen. Jupiter possesses one of the strongest magnetic fields in the entire solar system, stretching millions of kilometers into space. This powerful field is likely generated by the movement of metallic hydrogen deep inside the planet. As the planet spins, flowing metallic hydrogen generates electric currents, and those currents create a magnetic field. Because the metallic layer is so large and so mobile, the resulting field is immense, more than 20,000 times stronger than Earth's. Saturn too likely owes its magnetic field to the swirling metallic hydrogen hidden beneath its clouds. The presence of metallic hydrogen does more than shape magnetic fields. It influences the behavior of storms, the distribution of heat, and the evolution of the planets themselves. The deep interior is constantly in motion with large convection currents rising and falling through the metallic layer. These motions transport heat outward, feeding the long-lived storms seen at the surface. They also slow and shape the planet's rotation in subtle ways, giving rise to patterns that scientists continue to study. Because metallic hydrogen exists only under extreme pressure, scientists have long been curious whether it could be created on Earth. Producing it requires mimicking the conditions inside a gas giant. Pressures are so extreme that even the hardest materials struggle to withstand them. One method involves diamond anvil cells, devices where two flawless diamonds press a tiny sample of hydrogen between them. As pressure increases, the sample is squeezed with forces stronger than those found anywhere else on Earth. Some experiments have claimed to produce metallic hydrogen in this way, though the results remain debated, partly because the material can vanish if the pressure drops even slightly. Other experiments use shock compression, sending a powerful wave through hydrogen to momentarily create the necessary pressure. These experiments produce metallic hydrogen for mere fractions of a second, just long enough to gather hints about its behavior. Studying metallic hydrogen is difficult because it refuses to remain metallic unless the pressure remains extreme. When the conditions ease even slightly, hydrogen reverts to its more familiar form. The fleeting nature of the state makes it challenging to confirm its properties, to observe it directly, or even to collect proper measurements. There is hope that once fully understood, metallic hydrogen could help scientists unravel new questions about matter, magnetism, and planetary interiors. Some researchers even speculate that a stable form could be used as a superconductor or as a powerful form of rocket fuel. Though this remains highly speculative, still, the mere possibility reveals how many mysteries are wrapped up in this unusual state. The connection between metallic hydrogen and planetary interiors highlights how much we still have to learn about the giant worlds in our solar system. The behaviors we observe at their surface, the storms, the belts of clouds, the swirling colors, are simply expressions of the immense forces operating deep below. Metallic hydrogen provides the link between what happens at the heart of a planet and what we see in its sweeping atmosphere. The deeper we look, the more we realize that these planets are not simply gas-filled spheres, but dynamic worlds shaped by extreme physics. There is something soothing in imagining this hidden ocean inside Jupiter. Far beneath the lightning storms and cloud tops, beneath the striped layers and swirling bands, a vast sea of metallic hydrogen moves slowly and silently, following the planet's rotation. Its currents glide with a rhythm set by gravity and heat, turning an invisible interior into a quiet engine that powers the world above. No light reaches this deep, yet the material itself may shine faintly, reflecting what little light could reach it in smooth metallic gleams. Saturn hosts a similar world within, though softer and more muted, a calmer version of Jupiter's turbulent heart. Metallic hydrogen reminds us that matter can adopt forms that seem almost fantastical, forms that challenge our intuition and stretch the imagination. Hydrogen, the simplest element, capable of acting like a metal thousands of kilometers beneath a planet's surface, is proof that the universe prefers creativity over simplicity. It takes familiar ingredients and transforms them into extraordinary structures when the conditions become extreme. As you picture those deep planetary oceans filled with shimmering conductive hydrogen, it becomes easier to imagine the vastness and quiet complexity of the outer planets. What seems soft and hazy from afar hides a landscape of incredible pressure, intense heat, and matter behaving in ways that Earth can barely imitate. Metallic hydrogen is one of the clearest reminders that the universe keeps its most fascinating ideas tucked away in places we cannot easily reach, waiting for curiosity and patience to bring them gently into view. Our journey now takes us to another stellar remnant, one defined not by heat or fluidity, but by the ultimate stability of compressed quantum rules. At the end of a star's long and luminous life, something remarkable happens. After burning through its fuel over billions of years, after shining steadily across the darkness, and after swelling into a red giant in its final act, the star eventually releases its outer layers in a soft, drifting cloud. What remains after this quiet shedding is a core no larger than a planet, yet far denser than anything found on Earth. This leftover ember is called a white dwarf, and inside it, matter enters a state so unusual that its stability is governed not by heat or pressure in the familiar sense, but by the deep, quiet rules of quantum mechanics. This is degenerate matter, a form of matter held up not by motion but by the simple fact that electrons cannot be squeezed into the same place at the same time. To understand how extraordinary this is, imagine the core of a star compressing under its own weight. In the star's earlier life, the heat from nuclear fusion pushes outward, countering the pull of gravity. But once the fusion ends, gravity begins to win. With no new energy being produced to resist collapse, the star contracts. The material is squeezed tighter and tighter. Atoms are drawn inward as the volume shrinks dramatically. If this same pressure occurred inside an ordinary object on Earth, the atoms would break apart completely. But in the collapsing core of a dying star, something different takes hold. As the atoms are pushed together, the electrons become crowded. Under normal conditions, electrons move freely through space, occupying different energy levels and leaving ample room around each nucleus. But in a star's shrinking core, there is no room left. The electrons are squeezed into extremely tight spaces, filling every available state they're allowed to occupy. According to the rules of quantum physics, two electrons cannot share the same state. Once all the lowest energy states are filled, the electrons have no choice but to exert a pressure of their own, resisting further compression. This resistance is called electron degeneracy pressure, and it provides the support that keeps a white dwarf from collapsing completely. A gentle metaphor helps. Imagine a room gradually filling with people. First, there is plenty of space and everyone can spread out comfortably. As more people enter, they get closer. Eventually, the room becomes so full that individuals can no longer stand wherever they choose. They must occupy separate spots, unable to overlap. Even if everyone remains perfectly quiet and still, their very presence exerts pressure simply because there is no room left to move. Degenerate matter behaves similarly. Its pressure does not come from temperature or motion, but from the inability of electrons to be compressed beyond a certain point. Inside a white dwarf, this degenerate matter forms layers of astonishing density. A single teaspoon of white dwarf material would weigh tons on Earth, far beyond anything we can lift or imagine in the everyday world. Yet, despite this density, the white dwarf remains stable and quiet, shining faintly as it slowly cools. The glow we see is not from active fusion, but from leftover heat trapped during the star's earlier life. Over billions of years, the white dwarf radiates this warmth into space, dimming gradually until it becomes a cold, dark remnant known as a black dwarf, a theoretical object that has not yet formed anywhere in the universe, because the cosmos is still too young for white dwarfs to cool that far. Surprisingly, the interior of a white dwarf is not simply a dense gas. Over time, as it cools further, the ions inside begin to arrange themselves into an enormous crystal. The entire star gradually forms a giant lattice, a single crystalline object far larger than any structure nature has created elsewhere. This crystalline nature means white dwarfs are literally stellar diamonds in the sky. Certain white dwarfs that have cooled sufficiently show evidence of this crystallization through subtle changes in their pulsations and cooling rates. When astronomers study these patterns, they are effectively sensing the structure of a solid star core billions of years old. The existence of electron degeneracy pressure also explains why white dwarfs cannot grow beyond a certain limit. If too much mass accumulates, perhaps through material falling in from a companion star, the gravitational pressure eventually overwhelms the electron degeneracy pressure. The electrons cannot resist further compression beyond a specific point. Once that threshold is reached, collapse becomes inevitable. This limit, known as the Chandrasekhar limit, marks the boundary where a white dwarf can no longer remain stable. If the mass exceeds this limit, the star collapses into an even denser object, such as a neutron star, or in some cases detonates in a thermonuclear explosion that becomes a Type I supernova. This dramatic event spreads heavy elements across space, seeding the galaxy with the ingredients for planets, life, and future stars. Yet even with this potential for collapse, most white dwarfs live extraordinarily peaceful existences. They float silently through space, often paired with another star or drifting alone. Their small size and faint glow make them easy to overlook, but they are far from rare. Many stars in the night sky will eventually become white dwarfs when their fuel runs out. Even our own sun is destined for this transformation, leaving behind a small, dense core glowing gently for more time than has already passed since it first formed. The atmosphere of a white dwarf is also remarkable. Because the gravity at the surface is so strong, heavier elements sink inward, leaving the outermost layers composed almost entirely of hydrogen or helium. This creates the illusion of simplicity, a smooth, uniform exterior, even though the interior is astonishingly complex. Observing these outer layers allows astronomers to infer the temperature and age of the star, giving clues about its cooling process and history. There is a quiet poetry in imagining a white dwarf shining in darkness, a tiny ember floating in the vastness of space. No surface storms rage, no flares burst from its shell, no new fusion takes place within. Instead, it cools slowly, steadily, patiently, like a cosmic coal that refuses to fully extinguish. Its light is soft, its energy calm, yet the physics inside remains intense and extraordinary. Beneath the still surface lies matter governed by the strictest rules of quantum mechanics, packed into densities that defy intuition, supported by principles that prevent collapse, even when gravity tries its hardest to compress it further. Degenerate matter reminds us that the universe holds forms of stability we rarely encounter. It shows that even after a star has burned its last atom of fuel, its remains can settle into a new equilibrium shaped not by heat, but by the quiet arrangement of electrons. It is a state where matter finds balance under extreme conditions, producing objects that glow gently for billions of years. As you imagine a white dwarf hanging alone against the backdrop of the galaxy, its crystalline heart cooling and its faint light drifting outward, it becomes clear that even the remnants of stars carry beauty. They embody the universe's habit of creating new forms from endings and weaving the strange rules of the quantum world into the grand architecture of the cosmos. Now we explore a state that pushes this compression even further, where gravity crushes electrons and protons into an entirely new kind of matter. When a massive star reaches the end of its life, gravity takes over with a force so overwhelming that it reshapes matter itself. After the star has burned through its nuclear fuel, after it has collapsed through its white dwarf stage and pushed past the limits of electron support, the inward pull becomes unstoppable. Electrons are driven into protons with such intensity that they merge, forming neutrons and releasing neutrinos that stream away into space. What remains after this extraordinary collapse is one of the densest objects the universe can create, a neutron star. Inside it, matter enters a state so compressed, so quiet and unyielding that it behaves like a single enormous atomic nucleus. The process that forms neutron matter begins with pressure unlike anything you can imagine. In an ordinary star, electrons fill the space around atomic nuclei, providing structure and stability. But as the core collapses, that space disappears. The electrons are forced closer and closer to protons until they combine. What was once a mixture of particles becomes a vast, dense fluid of neutrons packed so tightly that a teaspoon of neutron star material would outweigh mountains. This is neutron matter, a form of matter held together by forces normally found only in the tiny centers of atoms, now stretched across an object 20 kilometers wide. The outer layers of a neutron star form a crust unlike anything on Earth. At the very surface, the crust begins with atomic nuclei packed far more tightly than in any terrestrial solid. These nuclei sit in a sea of electrons, forming a rigid crystalline structure. But as you move deeper, the pressure increases and the nuclei become more exotic. They become richer in neutrons, heavier, stranger, reshaped by the intense compression. Eventually, the nuclei can no longer remain intact. They begin to merge into one another, forming elongated structures that stretch into sheets and twist into tubes. This middle region is known as nuclear pasta, a name that brings gentle humor to one of the universe's most extreme materials. The shapes resemble lasagna sheets, spaghetti strands, gnocchi-like clusters and other forms, all sculpted by the delicate balance between nuclear attraction and electrical repulsion. Although the comparison to pasta is light-hearted, the physics behind it is profound. These forms minimize the system's energy under colossal pressure, arranging themselves in patterns that are both intricate and robust. This nuclear pasta may be the strongest material in the universe, capable of withstanding forces beyond imagining. Below this pasta layer, the crust dissolves entirely into a sea of neutrons. This inner region behaves like a vast quantum fluid, where neutrons drift together with a unity that resembles the behavior of superfluids. The density here is so high that the distinction between separate atoms disappears. Instead of countless individual particles, the matter behaves like one continuous, densely packed medium. It is as if the entire inner structure of the neutron star has fused into a single entity bound together by nuclear forces that dominate everything else. The surface of a neutron star may seem calm from a great distance, but the crust is subject to tremendous stresses. The star rotates sometimes hundreds of times per second, dragging its magnetic field with it. The magnetic forces, the internal pressure, and the rigid crust all interact, building tension that can occasionally release in the form of starquakes. These quakes are sudden adjustments in the crust, similar to earthquakes on Earth, but far more powerful. When the crust gives way, the neutron star's rotation can change ever so slightly, causing tiny sudden jumps in its spin rate. These events, known as glitches, reveal the dynamic, shifting nature of the star's interior. Yet, despite their intensity, these quakes remain wrapped in silence across the vacuum, their effects detectable only through the star's altered rhythm. Neutron matter behaves like a gigantic atomic nucleus because the density is so extreme. In a typical atom, neutrons and protons cluster tightly in the center, forming a nucleus surrounded by electrons. In a neutron star, this concept scales upward dramatically. The entire star behaves like an enormous nucleus held together by gravity rather than by electromagnetic attraction. The neutrons are packed so closely that quantum forces dictate how they arrange themselves, leaving practically no empty space between them. It is a world dominated by nuclear physics on a cosmic scale. Despite the overwhelming density, neutron stars are difficult in their way. Their structure depends on a careful balance between gravity pulling inward and neutron degeneracy pressure pushing outward. This pressure arises from the same fundamental principle that supports white dwarfs, but applied to neutrons rather than electrons. Neutrons, like all particles of their kind, cannot occupy the same state. When squeezed tightly enough, they push back. This resistance halts the collapse, creating a stable structure, but only up to a point. If the mass grows too large, not even neutron degeneracy can resist the inward pull. The star collapses further, forming a black hole. The threshold between a neutron star and a black hole is one of the universe's most dramatic dividing lines. Imagining the interior of a neutron star is like stepping into a realm where everyday intuition fades. Temperatures soar into the millions of degrees, magnetic fields twist and pulse with staggering strength, and matter exists in forms that lie far outside human experience. Still, images can still feel peaceful. Picture a sphere no wider than a large city resting silently in the darkness. Inside, neutrons drift in dense coordinated motion. Sheets of nuclear pasta hold their shape beneath immense pressure. The faint glow of heat escapes slowly into the vacuum, shining like a distant lantern against the blackness of space. Neutron stars also play a quiet role in the history of the cosmos. When two neutron stars orbit each other closely, they can eventually collide, releasing extraordinary amounts of energy and creating heavy elements such as gold and platinum. These collisions send ripples of gravitational waves across the universe, leaving subtle vibrations that observatories, on Earth, have only recently learned to detect. Even in their destruction, neutron stars enrich the universe with new materials, seeding galaxies with the elements that later form planets and life. Neutron matter is one of the most extreme states of matter known, shaped by pressures that squeeze the familiar world into something almost abstract. Yet it follows the same basic rules that govern atoms, elements, and matter everywhere. It reveals what happens when those rules are pushed to their limits, showing that even the tiniest principles of quantum mechanics can sculpt objects as vast and dense as stars. In the end, neutron stars are a reminder that the universe is filled with quiet extremes. They sit like cosmic bookends to the story of stellar evolution, holding within them a state of matter that exists nowhere else. A world where particles are pressed into unity under gravity's strongest hand. Their dense interiors whisper of the strange beauty that emerges when matter is pushed beyond the edge of the ordinary, settling into forms that stretch the imagination, yet obey the deepest laws of nature. We now move from the collapsed remnants of the universe to its earliest, hottest moments, in the earliest moments of the universe, before stars, before atoms, before even the simplest structures had time to assemble themselves, matter existed in a form so hot, so dense, and so energetic that the familiar building blocks of protons and neutrons could not yet take shape. It was a state where the tiniest constituents of matter drifted freely in a glowing sea of primordial motion. This state is called quark-gluon plasma, and it represents the most energetic form of matter known. To understand it is to take a gentle step back toward the beginning of everything, into an era when the universe was only a fraction of a second old and filled with a warm, radiant haze. Under ordinary conditions, quarks never roam freely. They clump together in groups, forming protons, neutrons, and other particles. These quarks are bound by the strong nuclear force, carried by particles called gluons that act like tiny, ever-present threads pulling the quarks inward. The bonds are so strong that quarks cannot escape individually. They remain tightly confined inside the particles they form, but if the temperature becomes high enough, those bonds weaken and the quarks begin to move independently, no longer constrained to remain in their usual trios. The gluons, too, become free to drift, interacting in a fluid of their own. This is quark-gluon plasma, a phase of matter where the fundamental components of nuclear particles spread out and mingle like droplets in a smooth, radiant soup. The universe existed in this state during its first moments when temperatures were trillions of degrees and densities were extreme. At that time, the cosmos was a glowing, fog-like medium without structure. But as it expanded, it cooled. Within the first second, the temperature dropped enough for quarks to become trapped again inside newly formed protons and neutrons. This transition marked the beginning of the familiar atomic world. As time continued, more complex structures formed, eventually leading to stars, planets, and all the matter around us. Yet, the memory of that primordial state remained encoded in the universe's earliest light, a quiet record of the moment when quark-gluon plasma condensed into the particles we know today. Although this plasma naturally existed only at the dawn of time, scientists have found ways to create tiny droplets of it here on Earth. Modern particle colliders, such as the Large Hadron Collider and the relativistic heavy ion collider, accelerate heavy atomic nuclei to tremendous speeds and then bring them into head-on collisions. The energy released in these collisions is enough to recreate the conditions that existed just after the universe began. For a brief instant, the quarks and gluons break free, forming a tiny pocket of quark-gluon plasma, no larger than a subatomic speck. These droplets last for only millionths of a billionth of a second, but during that short time, they reveal behaviors that are both surprising and deeply instructive. One of the most unexpected discoveries is that this plasma behaves not like a chaotic gas, as many scientists once predicted, but like an extraordinarily smooth liquid. It flows with almost no internal resistance, moving with elegance rather than violence. Ripples of motion pass through it with remarkable fluidity, as though it were a single coordinated entity rather than a swarm of independent particles. This makes quark-gluon plasma one of the most perfect liquids ever observed, displaying an effortless flow that seems almost at odds with its extreme temperature. The reason for this exquisite behavior lies in the strong nuclear force. Even though the quarks and gluons are no longer confined inside protons and neutrons, they still interact strongly with one another. These interactions create a network of subtle connections throughout the plasma, binding the motion of one particle to the behavior of its neighbors. The result is a fluid that moves collectively with remarkable coherence. Instead of particles bouncing chaotically, the plasma forms patterns of flow, waves, and vortices as though it were a sheet of water responding to a gentle touch. This near-perfect fluidity makes quark-gluon plasma fascinating to study. It helps physicists understand the strong nuclear force in new ways, revealing how this fundamental force behaves under the most extreme conditions possible. Observing how the plasma expands, how it cools, and how it transitions back into ordinary particles gives clues about the early universe's evolution. Every experiment reconstructs a tiny, fleeting echo of the first moments of cosmological history, allowing scientists to peer into a time otherwise inaccessible. In the quiet of a laboratory, these collisions create bursts of energy that carry the soft imprint of the universe's beginnings. The detectors surrounding the collision zones catch the faint trails left by the particles as they form and scatter, revealing what happened during those unimaginable fractions of a moment. Each droplet of quark-gluon plasma provides a snapshot of conditions that shaped everything that followed. The data offers glimpses of patterns that resemble the waves in a pond or the swirl of currents in a river, scaled down to an incomprehensibly small size and heated to extraordinary temperatures. Reflecting on this plasma invites a sense of cosmic calm. Imagine the universe in its infancy filled with a warm, glowing haze of quarks and gluons drifting freely, unconfined and unstructured. There were no atoms, no molecules, no stars, only a smooth, luminous fluid filling all of space, gently expanding as the first fractions of time passed. This peaceful glow contained the seeds of everything that would emerge later, the galaxies, the planets, the life that would study the universe billions of years afterward. Even today, when scientists recreate this ancient state, the imagery remains soothing in its own way. These droplets, though incredibly hot, behave with a softness that feels almost paradoxical. Instead of erupting violently, they flow smoothly, showing that even at the extremes of temperature and energy, nature can choose elegance over chaos. The plasma reminds us that the universe's foundations were laid in a moment of gentle transformation where cooling allowed structure to form and patterns to emerge. Quark-gluon plasma is the bridge between the primordial and the present. It represents matter in its most fundamental form before it settles into the particles that shape the world around us. It teaches that even the smallest components of matter have stories rooted in the earliest light of the universe, and that by recreating these ancient conditions, we can explore the delicate interplay of forces that gave rise to the cosmos. In this glowing fluid state, we see not only the beginning of time, but also the extraordinary continuity that links that beginning to every atom that exists today. We now turn to an opposite kind of ethereal matter, one defined not by intense compression, but by extreme expansion. When an atom is calm and unexcited, its electrons sit close to the nucleus, held in gentle orbits that give each element its familiar size and character. But when an atom absorbs energy carefully, delicately, and in just the right amount, one of its electrons can be lifted far away from the nucleus, placed into a huge expanded orbit. The atom swells dramatically, sometimes reaching sizes thousands of times larger than normal. These oversized, fragile atoms are called Rydberg atoms. And when many of them gather together, they can form an unusual, airy state of matter known as Rydberg matter. It is a state where atoms drift in loose clusters, each expanded like a softly inflated bubble interacting gently across distances far larger than in ordinary matter. The Rydberg atom idea starts with electrons. In a typical atom, the electron remains close to the center, bound tightly by the electric pull of the nucleus. But when energy is added through light or heat or precisely tuned electromagnetic waves, the electron can be nudged into a higher energy level. In this elevated state, the electron's orbit stretches outward, widening like a balloon, slowly inflating. The atom becomes enormous by atomic standards. Its boundaries spread outward into a hazy sphere of influence. Even though the electron remains bound to the nucleus, the distance between them becomes so large that the outer region of the atom is almost empty. The atom takes on a ghostly, diffuse character, as though it were made of soft mist rather than solid structure. When many of these swollen atoms gather, they can form Rydberg matter, a delicate cluster of expanded atoms that interact in unusual ways. Unlike typical solids or liquids, where atoms press closely and vibrate within tightly packed neighborhoods, Rydberg atoms keep one another at a distance. Their expanded electron clouds overlap gently, forming weak connections that allow the atoms to arrange themselves into loose patterns. In some cases, they form shapes reminiscent of small lattices, but far more spacious and ethereal than anything found in ordinary materials. The distances between atoms in Rydberg matter can be hundreds or even thousands of times larger than the separations in conventional solids. This spaciousness changes everything about how the material behaves. The atoms interact with one another over long distances because their electron clouds are so large. A small shift in one atom can influence others nearby, creating coordinated patterns of behavior that feel almost choreographed. These long-range interactions allow scientists to study quantum effects that are normally hidden at tiny scales. In ordinary atoms, the quantum rules governing electrons and nuclei unfold at distances too small to see or manipulate easily. But in Rydberg, these effects extend into a larger, more accessible space. This makes it an ideal system for exploring quantum behavior in ways that are easier to observe and control. The interactions between Rydberg atoms are among the most intriguing parts of this state of matter. Because their electrons sit so far from the nucleus, the atoms become incredibly sensitive to one another's presence. They can shift energy levels, repel or attract, or even block one another from becoming excited into higher states. In these clusters, a change in one atom can prevent nearby atoms from absorbing additional energy. This effect, called the Rydberg blockade, creates an environment where atoms behave collectively, responding to stimuli as a group rather than as isolated individuals. This makes Rydberg matter a promising tool for building controlled quantum systems, including early forms of quantum computers where the behavior of individual atoms must be guided with careful precision. There is a gentle beauty in imagining clusters of Rydberg atoms drifting through near nothingness. Instead of the tight, rigid structures we associate with solids or the flowing, interwoven forms of liquids, these atoms float at comfortable distances, barely touching. Their interactions occur through faint, extended fields rather than direct contact. The atom's size is so exaggerated that the boundary between emptiness and structure becomes thin, almost transparent. It is matter stretched toward its limit, expanded into a form that borders on pure space. Studying Rydberg matter also reveals how easily atoms can be encouraged to behave in unusual ways when the conditions are just right. The only requirement is a gentle touch of energy. Not enough to strip the electron away completely, but enough to raise it into the wide, quiet orbit that defines the Rydberg state. Once a collection of these atoms forms, its behavior becomes a window into how matter responds when stretched toward delicacy rather than compressed toward density. Rydberg matter behaves neither like a solid nor a gas in the familiar sense. It forms clusters that hold together loosely with energies so subtle that temperature changes can nudge them apart. Because the atoms are so weakly bound, the material is extremely fragile. Even slight disturbances can disrupt the clusters, causing the atoms to return to their smaller, tighter configurations. But this fragility is also part of what makes the state fascinating. It shows how matter can hover on the edge of instability, balanced in a region where quantum effects dominate, but do so gently, gracefully. Scientists are drawn to Rydberg matter, not just because of its unusual structure, but because it provides a rare opportunity to explore the quantum world in slow motion. In ordinary atoms, changes occur so quickly and on such small scales that they blur together. But in Rydberg atoms, the distances are so large and the motions so slow that the quantum processes can be mapped more clearly. This allows researchers to watch transitions, interactions, and collapses in ways that reveal deeper insights into how matter behaves at the smallest scales. These expanded atoms also promise future technologies. Their sensitivity makes them ideal for detecting small variations in electric fields or for creating controlled quantum states that can store or transmit information. Because they interact so strongly across long distances, they could help create networks of atoms that work together in coordinated patterns, forming the foundation for quantum devices that rely on collective behavior rather than isolated particles. Beyond the scientific potential, Rydberg matter invites a more quiet, contemplative reflection. It shows that matter does not always move toward compactness or order when energy is added. Sometimes energy causes expansion, softness, and diffusion. It allows atoms to stretch outward into wide orbits that feel almost otherworldly, occupying regions of space that would normally remain empty. In this expanded form, atoms drift like gentle bubbles held together by forces so faint they seem barely present. Picture them floating in a dark vacuum chamber, each glow faintly from the energy that holds its electron aloft. Picture the loose cluster they form, wide and airy, so diffuse that you could pass through it without noticing, yet so structured that each atom responds to its neighbors from afar. Rydberg matter reminds us that even the simplest atoms can be coaxed into extraordinary shapes. It reveals a side of the quantum world where matter becomes light and delicate, stretched into forms that challenge our intuition. And like many hidden states of matter, it shows that the boundaries between the familiar and the strange are far softer than they appear, waiting quietly for the right conditions to unfold. Our next state embraces an even stranger type of organization, one where matter finds stability not in space but in a precise repeating rhythm in time. In the familiar world, everything eventually settles. A pendulum slows, a tuning fork's vibration fades, a cup of water stirred into a whirlpool gradually smooths into stillness. This gentle return to calm is woven into the fabric of time itself. Physical systems tend to lose motion as energy spreads and dissipates. They settle into equilibrium where nothing repeats endlessly without being pushed. But in the strange, quiet corners of modern physics, researchers have discovered states of matter that refuse to settle in this traditional way. Instead, they fall into rhythms, soft, steady patterns that repeat in time. Not because energy is added, but because of the unusual way the system organizes itself. These are called time crystals, a name that sounds like something from a fantasy novel, yet describes a very real and deeply intriguing phase of matter. To understand the beauty of a time crystal, it helps to begin with an ordinary crystal. In a solid crystal, atoms arrange themselves in a repeating pattern that stretches across space. Each atom sits in a specific place, forming a regular lattice that continues in every direction. Snowflakes, salt crystals, and diamonds all follow this repeating spatial structure. The order is calm and stable, arising naturally as the lowest energy configuration. Time crystals extend this idea into another dimension. Instead of repeating in space, a time crystal repeats in time. Its internal state returns to the same configuration at regular intervals, like a soft and steady pulse. The remarkable part is that this rhythm appears without requiring energy to be added from outside. It is not like the ticking of a clock or the swinging of a pendulum, which need occasional pushes to keep going. Instead, the time crystal maintains its rhythm even in complete isolation, as though it has found a way to organize itself into an endless temporal pattern. The system oscillates between configurations with perfect regularity, a gentle back and forth that continues indefinitely. In a sense, the material gains its stability not from stillness but from motion that never fades. This behavior seems to contradict the intuition that physical systems should settle into equilibrium. Time crystals do not do that. They exist in what is called a non-equilibrium phase, where the system is constantly in motion yet perfectly stable. The atoms or spins within the material lock into a rhythm dictated by the system's internal rules, rather than by external energy sources. The rhythm is not arbitrary. It is tied to the natural frequencies of the interactions within the system, establishing a repeating pattern that endures as long as the conditions remain right. One way to picture this is to imagine a gentle metronome that never slows down, no matter how long it has been ticking. Even if left entirely alone, it continues marking time with perfect consistency. Another image is a line of people passing a soft pulse down the row. Instead of fading as it moves, the pulse returns again and again, as though the group is tuned into a shared rhythm that cannot be disrupted. Time crystals embody this kind of temporal order, but at the level of atoms and quantum states. The key to their creation lies in carefully controlled quantum systems, often involving interacting spins or ions held in precise arrangements. These systems are driven so that their internal interactions create periodic behavior. However, the truly astonishing feature is that the period of the crystal's rhythm can be different from the period of the driving force. For instance, if the system is nudged at one rhythm, the internal structure might respond at half that rate or double it, establishing a stable pattern that is not merely a copy of the external drive. This is known as breaking time translation symmetry, a concept that underpins the entire idea of time crystals. In normal systems, time passing does not change the underlying rules. The laws remain the same from moment to moment, but in a time crystal, the system organizes itself so that it repeats only after a certain number of time steps. It is as though the system says gently and persistently that it prefers a rhythm different from the one imposed upon it. This spontaneous organization into a repeating temporal structure is what makes time crystals such an exciting and unusual state of matter. The discovery of time crystals is more than a curiosity. These structures have potential applications in quantum technology, where stability and coherence are precious resources. Quantum computers rely on delicate states that must be preserved for meaningful calculations. Time crystals offer a new kind of robustness, as their rhythmic structure makes them resistant to certain types of disturbance. Because the system naturally maintains its pattern, it may serve as a foundation for storing information in a way that is less prone to fading or decoherence. In this sense, time crystals could one day become the quiet guardians of quantum data, keeping information safe within their repeating rhythm. Another potential use is precision measurement. Systems that maintain perfect periodicity can be useful for timing, sensing, or detecting small changes in the environment. A rhythm that cannot fade, even in the presence of noise, offers a level of stability that could enhance future technologies. The scientific community is only beginning to uncover these possibilities, but the underlying principles suggest that time crystals may become an important tool in understanding and harnessing quantum behavior. Despite their name, time crystals are not glittering gemstones or shimmering spheres. Instead, they exist in controlled laboratory environments, often created with ions held in electromagnetic traps or qubits, arranged in carefully tuned quantum setups. A diamond's visual beauty lies in its spatial order. The beauty of a time crystal lies in its temporal order, a rhythm, a pulse, a gentle and persistent returning. It is a beauty that unfolds not in the shape the material takes, but in the pattern it maintains through time. Picture a time crystal as a soft flicker repeating endlessly in the quiet of a laboratory chamber. Each repetition is identical to the last, following a schedule set not by an external push but by the internal conversation among quantum particles. They follow their own choreography, stepping through the same sequence again and again, as though time itself has become part of the structure of matter. The idea that matter can hold rhythm without energy seems almost poetic. It hints that the universe has ways of organizing itself that are not immediately visible in everyday experience. While most physical systems drift into stillness, time crystals remain in motion, their softness arising from a cycle rather than calmness. They show that the flow of time, usually perceived as steady and unremarkable, can be shaped into patterns at the quantum level. As you imagine this gentle ticking, this endlessly repeating pulse, it becomes clear why time crystals feel so surprising and so serene. They remind us that the boundaries of matter are not only spatial but temporal, and in the quiet repetition of a time crystal's rhythm, there's a sense of matter embracing time itself, weaving patterns into its flow with a grace that continues without ever needing to be renewed. This idea of subtle, enduring motion also defines our next state, where magnetic components refuse to freeze into a final, rigid arrangement. In most familiar magnetic materials, the tiny magnetic moments inside, the spins, prefer to align in neat, orderly patterns. They tilt toward a shared direction, forming smooth fields that remain steady over time. This is why magnets hold their shape, why compass needles point north, and why magnetic patterns can be recorded and preserved. But in some rare materials, the structure of the crystal forces these magnetic spins into positions that cannot all be satisfied at once. The geometry itself creates a puzzle with no perfect solution. These materials are known as spin ices, and they form a quiet, restless state where the spins never settle completely, wandering softly through endless rearrangements even at low temperatures. To understand why this happens, it helps to picture the layout of certain crystals. In ordinary magnets, spins sit on a lattice that allows them to align comfortably with their neighbors. But in spin ice, the atoms are arranged in shapes that create unavoidable conflict. The most common structure is a network of tetrahedra, tiny four-pointed shapes joined together in a repeating three-dimensional pattern. Each corner of a tetrahedron hosts a magnetic moment, a miniature arrow pointing in a direction dictated by the atom's surroundings. The geometry of the tetrahedron demands that the spins follow rules resembling the behavior of water molecules in frozen ice. In the same way that two hydrogen atoms point inward toward the oxygen in each water molecule, spins in spin ice prefer a two-in, two-out arrangement inside each tetrahedron. The trouble begins when these tetrahedra connect. What satisfies the rule in one part of the structure creates tension in another. A spin pointing inward to satisfy one tetrahedron might need to point outward to satisfy the next. No matter how the system tries to arrange itself, some part of the structure will remain frustrated. The spins cannot all find positions that make every neighbor happy. They settle instead into a state where many configurations are nearly equal in energy, each one only slightly different from the last. This creates a landscape of possibilities rather than a single, stable arrangement. This frustration gives spin ice its name and its character. Like water ice, where the hydrogen atoms can adopt many different local arrangements, spin ice contains countless possible configurations that satisfy its rules. The spins shift gently among these possibilities, wandering in patterns that never fully freeze. Even as the temperature drops toward absolute zero, the system retains a quiet dynamism. The spins do not lock into one pattern but continue drifting as though unable to decide on a final arrangement. Within this restless behavior emerges something even more surprising: excitations that behave like magnetic monopoles. In everyday physics, monopoles, isolated north or south magnetic poles, do not exist. Every magnet has both a north and a south pole. They always come in pairs. But in spin ice, when the spins shift in certain ways, they create disturbances that act like isolated magnetic charges. If a spin flips, it can create a pair of defects, one that behaves like a north pole, the other like a south pole. These defects can move independently through the lattice, traveling along paths defined by further spin flips. The result is a material where effective monopoles drift quietly through the structure, interacting in ways that mimic the behavior of magnetic charges. These monopole-like excitations add an extra layer of richness to spin ice. They make the material feel alive in a gentle, almost fluid sense. The magnetic landscape shifts softly as these excitations migrate, forming patterns that seem to breathe or gently ripple beneath the surface. In laboratory experiments, researchers can detect these movements, watching the emergent monopoles behave as if they were real particles. Their paths weave through the spin ice in a constant slow dance, leaving trails of altered magnetic orientation behind. The presence of frustration also influences how spin ice responds to changes in temperature and magnetic field. Instead of transitioning cleanly between ordered and disordered states, the structure resists settling. Small changes can ripple through the lattice, rearranging patterns in subtle and surprising ways. The system behaves like an intricate puzzle whose pieces are always shifting, always searching for balance, yet never reaching complete harmony. This unsettled nature feels oddly peaceful when viewed from a cosmic perspective, a reminder that not all stability arises from perfect order. Some forms of matter are content to exist in a state of perpetual near equilibrium, drifting calmly within a landscape of unresolved tensions. Despite its complexity, the imagery of spin ice can be soft and calming. Imagine a vast crystalline forest, each magnetic moment a tiny arrow gently turning, nudged by its neighbors, guided by rules that clash just enough to keep the landscape in motion. Patterns emerge briefly and dissolve again, replaced by new arrangements that shift and settle like wind-stirred leaves. The restlessness is subtle, never violent, a quiet rearrangement happening over and over on the smallest scales. This gentle dynamism offers a powerful way for scientists to explore concepts like frustration, emergent behavior, and collective motion. It shows how simple rules applied in the right geometry can produce outcomes far richer than expected. While no individual spin dictates the whole behavior, their interactions combine into patterns and excitations that behave like entirely new entities. This is the heart of emergent physics. The idea that the whole can behave differently from the sum of its parts. Spin ice has also sparked interest for potential technological applications. The monopole-like excitations may one day help researchers understand how to store and move information in new ways. The material's sensitivity to small magnetic changes could lead to advances in magnetic devices or quantum technologies. But even without these possibilities, spin ice stands out as a quiet reminder that matter does not always choose simple equilibrium. Sometimes it balances on the edge of competing tendencies, creating structures that are stable precisely because they never fully settle. As you imagine the interior of spin ice, picture a calming landscape of shifting magnetic arrows moving not with urgency, but with a slow, deliberate rhythm. Each shift opens new possibilities. Each configuration is a gentle compromise in an intricate lattice. It is a state defined not by stillness but by soft perpetual change, revealing yet another way the universe creates order from tension and beauty from complexity. This inability to freeze is taken to its most extreme quantum limit in our next, even stranger state of matter. In most magnetic materials, cooling brings order. As the temperature drops, the chaotic jostling of atoms softens and their tiny magnetic moments begin to line themselves up. Some align in the same direction, forming neat ferromagnets. Others settle into alternating patterns, creating gentle antiferromagnets. Either way, the cold encourages stillness. Spins freeze into stable arrangements like dancers finding fixed positions at the end of a performance. But there are rare materials where this freezing never happens, not even at temperatures so low that motion almost disappears. Instead, the spins continue to fluctuate softly, refusing to lock into a single pattern, drifting through a quiet choreography of constant change. These states are known as quantum spin liquids, and they offer one of the most serene and surprising stories in condensed matter physics. The term liquid may seem strange at first. These materials are not fluids flowing across a surface. They are solid by every outward appearance, but inside them, the spins, the tiny magnetic arrows carried by electrons, behave as though they are part of a liquid. They never settle, never freeze, never choose a final arrangement. Even as the temperature approaches absolute zero, the spins remain in motion, shifting in patterns guided by quantum rules rather than by thermal energy. The restlessness is delicate, subtle, and deeply unusual. To understand why this happens, imagine a network of spins arranged on a lattice with interactions that cannot all be satisfied at the same time. Each spin wants to align or anti-align with its neighbors in specific ways, but the geometry makes it impossible for every spin to achieve its preferred relationship. This frustration is similar to the behavior seen in spin ice, but here the frustration runs deeper, woven into the quantum structure itself. Instead of settling for any of the nearly acceptable arrangements, the system chooses a different solution. It embraces superposition. Spin does not choose one configuration, they explore them all at once, forming a quantum state where many different arrangements coexist in harmony. This quantum coexistence produces long-range entanglement, one of the most intriguing features of quantum spin liquids. Entanglement connects spins in ways that are not local or limited by distance. A change in one part of the system can influence a distant part, not through motion or signals, but through the underlying quantum structure. It is as though the spins whisper to one another across the lattice, maintaining relationships that remain intimate even across space. These long-range patterns give the quantum spin liquid its fluid-like nature. They create a constantly shifting magnetic environment where no single arrangement dominates. One way to picture this is to imagine a vast, quiet lake. Instead of freezing in winter, the water remains liquid, its surface gently rippling in slow, soft waves. The ripples do not fade entirely, and the lake never settles into perfect stillness, even though the temperature has dropped far below the point where ordinary water would turn to ice. A quantum spin liquid behaves this way in the space of magnetism. The spins form gentle, persistent fluctuations that continue even in deep cold, moving according to a rhythm shaped by entanglement rather than by heat. Because no conventional magnetic pattern forms, the system is said to lack magnetic order. This does not mean it is chaotic. On the contrary, the underlying structure is highly organized, but in a way that transcends simple patterns. Instead of forming rigid alignment, the spins weave together into a tapestry of correlations that extend across the entire material. These correlations are subtle, invisible to the naked eye, but they can be detected experimentally through scattering measurements that reveal a diffuse, distinctive signature, the fingerprint of a state that never freezes. Quantum spin liquids also cause excitations unlike those in ordinary magnets. Instead of disturbances propagating as waves of spin alignment or as simple flips of magnetic orientation, the excitations in these materials can behave like fractionalized particles. In some varieties of spin liquids, a single spin flip can break into two independent excitations, each carrying a portion of the original disturbance. These emergent particles drift through the lattice with behaviors entirely different from the electrons and spins that created them. They provide a glimpse of how collective quantum states can produce new forms of behavior that do not exist in simpler materials. The softness of quantum spin liquids, their refusal to settle, their delicate fluctuations makes them promising candidates for quantum technologies. Long-range entanglement is one of the key ingredients required for quantum computation, where information must be stored in ways that resist noise and decoherence. Certain types of quantum spin liquids are predicted to host topological states that could protect quantum information naturally, making them attractive for building stable, fault-tolerant quantum bits. In essence, the same qualities that allow the spin liquid to avoid freezing may help it safeguard delicate quantum data. This connection between spin liquids and quantum computing has drawn the attention of researchers around the world. If these materials can be created and controlled reliably, they may provide the foundation for new kinds of quantum devices. The idea is that information stored in the topology of a spin liquid, in patterns that span large regions rather than individual particles, could be inherently protected from disturbances. The gentle, unending fluctuations of the spin liquid would not erase this information, because the underlying structure is robust even when its surface-level behavior shifts gracefully from moment to moment. The search for real-world materials that behave as quantum spin liquids has led scientists to explore minerals with triangular or honeycomb-like arrangements of spins. These geometries naturally encourage frustration, creating the perfect environment for the liquid-like behavior to emerge. Several compounds have shown promising signs, including certain organic crystals, rare earth materials, and layered compounds, where spins reside on networks that resemble the geometry of a honeycomb. Each new discovery helps scientists understand how the delicate balance required for a spin liquid arises, and how it can be manipulated. Despite their complexity, the imagery of quantum spin liquids can be wonderfully soothing. Picture a vast field of tiny magnetic arrows, each one gently turning, never finding a final resting place. Instead of locking into rigid patterns, they drift endlessly through a quiet landscape shaped by interaction and entanglement. There is no chaos in this motion. It is soft, coordinated, and subtle, a quantum ballet unfolding in slow motion. The motions whisper of possibilities rather than decisions, of patterns that extend across space and time. This endless fluctuation challenges the intuition that cold brings stillness. It shows that at the very edge of freezing, quantum principles begin to dominate, allowing matter to find new forms of organization that defy classical expectations. Instead of choosing a single pattern, the quantum spin liquid embraces many, layering them into a harmonious blend of possibilities. The system becomes a place where motion is preserved not as turbulence but as quiet, enduring softness. So as the spins continue their quiet, shimmering dance, never freezing, never deciding, they create a landscape that feels almost cosmic in its softness. It is a world where motion never fades, where quantum rules write gentle patterns across the tiniest scales. Quantum spin liquids remind us that even in the deepest cold, the universe can still hum with a subtle ongoing warmth, not of heat, but of possibility. This idea of quantum protection through global structure is central to our final hidden state. In the world of everyday materials, behavior usually depends on ingredients. Copper conducts, rubber stretches, glass shatters, iron attracts magnets. Change the ingredients and you change the behavior. But there is a quieter, more subtle category of matter where the most important properties do not depend on the specific atoms involved. Instead, they depend on the shape of the system, not the visible shape like a square or a sphere, but the deeper, hidden shape, woven into the way electrons can move. These are states of topological matter, and they behave in ways that seem almost magical until you understand the role that shape and connectivity play at the quantum scale. Topology is a branch of mathematics that studies shape in its most flexible form. Under topology, a donut and a coffee mug belong to the same category because each has one hole. A sphere and a cube also belong together because neither has a hole. The specific curves or surfaces do not matter. What matters is how many holes, twists, or connections the object has. This idea sounds abstract, but it turns out that electrons in certain materials follow rules shaped not by precise atomic arrangement, but by the topological shape of the electronic structure within the material. In these systems, certain behaviors become incredibly robust, protected not by energy or purity, but by connectivity itself. One of the most fascinating examples is topological insulators. At first glance, this type of material seems contradictory. The interior behaves like an insulator, resisting the flow of electrical current, but the surface or edges behave like a smooth, nearly perfect conductor. This combination is not accidental. It occurs because the internal topology of the electronic states requires that any boundary between the interior and the external world holds special conducting states. These states cannot be removed, erased, or disrupted without fundamentally changing the topology of the material. They exist because of the shape of the system's quantum structure, not because of its chemical composition. Imagine a peaceful winding path along the coast. Even if the shoreline shifts slightly or weather erodes the land in places, the path still follows the same broad outline. It remains connected from one end to the other because its existence is shaped by the boundary between land and sea. Topological edge states behave similarly. They form paths along the edges of a material where electrons drift smoothly without scattering. Imperfections in the material, bumps, impurities, missing atoms cannot easily disrupt this motion. The electrons glide along as though following a quiet coastline, their journey protected by the underlying topology. This protection is what makes topological matter so unusual. In ordinary materials, impurities scatter electrons. A bump in a wire can redirect current, increasing resistance and causing heat to build. But in a topological system, the electrons traveling along the edges cannot simply turn around or scatter into the interior. Their motion is tied to the larger connectivity of the electronic landscape. To break their path entirely would require changing the topological shape of the system, something far more dramatic than simply adding impurities or shifting atoms. This robustness makes topological states incredibly stable, like a melody that continues even when individual notes are disturbed. The concept becomes even clearer when imagining simple topological objects. Consider a loop of string. The number of knots in the loop is a topological property. You can stretch the string, squeeze it, bend it, or twist it gently, and the number of knots will not change. To remove a knot, you must break the string or pass the loops through each other, significant changes that alter the overall connectivity. Topological matter works the same way. Its key features persist even when the material is bent, disturbed, or slightly altered. The edge pathways for electrons behave like knots in the fabric of the material's quantum structure. They cannot disappear without a dramatic shift in the system as a whole. Topological insulators are just one example. Other materials called topological superconductors host even more exotic states at their edges or boundaries. In these systems, electrical and magnetic behavior intertwine in ways that allow special quantum excitations to appear. These edge excitations can behave like particles that are not quite particles, carrying information in patterns that are protected by topology. Because they are resistant to disturbance, they may one day provide a stable foundation for quantum computing, storing and manipulating information in ways that are naturally shielded from noise. The resilience of topological states can feel almost uncanny. In ordinary systems, behavior often depends on details, the purity of a crystal, the temperature, the presence of imperfections. But topological matter smooths over many of these details. Its features arise not from the perfection of the system, but from the deeper connectivity within it. This makes the behavior feel as though it sits one level above the specific ingredients. It is as if the electrons agree to follow a set of global rules that cannot be easily violated locally. To picture this resilience, imagine a network of trails on a hillside. Many small paths twist and overlap, but there are certain main routes, sturdy, well-trodden trails that connect important points. Even if smaller paths are blocked by fallen branches or shifting soil, the main trails remain passable because they follow the natural contours of the hill. Topological pathways for electrons behave like those main trails. They are protected by the shape of the landscape itself, not by the fine details along the way. Minor disruptions cannot close them because the underlying terrain supports their existence. This idea becomes especially powerful when thinking about why information can travel along the edges of a topological material with such certainty. An electron moving along the boundary does not scatter backward, because doing so would require flipping its entire configuration, something that the topology forbids without major changes. This creates a kind of one-way motion, as though the electrons have committed themselves to moving along a protected route that cannot easily be disrupted. The path stays clear even when small obstacles appear. Because these states are defined by shape rather than microscopic detail, they hold remarkable promise for technology. Quantum devices often struggle with noise, tiny interactions that disrupt fragile quantum information, but topological quantum systems may store information in global patterns that cannot be altered by local disturbances. It is like writing a message not on paper where a single tear can destroy a word, but in the number of twists in a rope where you would have to unwind the entire structure to erase it. This inherent protection could lead to quantum computers that are far more stable and reliable. Beyond their technological potential, topological materials offer a softer, more philosophical reflection on how matter organizes itself. They show that nature does not always build stability through rigidity. Sometimes stability comes from openness, from the ability to bend without breaking, from patterns that persist because of how things connect, rather than how they're arranged. The robustness arises from the whole system working together, rather than from any individual part. Imagine electrons moving along the edges of such a material, sliding effortlessly through invisible corridors, shaped by the system's topology. No jagged imperfection alters their path. No small disruption causes them to lose their way. They follow routes carved not into the atoms but into the structure of the quantum landscape, moving with a softness that feels almost serene. The calm, unbroken journey of these electrons suggests a world where motion can remain gentle and assured, even in the presence of disorder. Topological matter reminds us that the universe has many ways of creating order. Some rely on symmetry, some on energy, some on structure, and some on connectivity so fundamental that it cannot be erased without transforming the object entirely. These states reveal that even in the smallest places, the spaces where electrons flow and quantum rules whisper, shape can matter more than substance. And in that quiet truth, there is a sense of elegance, a reminder that the deepest principles often arise not from the ingredients themselves, but from how they are woven together. Across all of these states, a broader picture of matter begins to appear, from the familiar solidity of everyday materials to the exotic phases that form only in extreme heat, deep cold, or powerful gravity. The behavior of matter reveals itself as remarkably adaptable. Classical states show how particles arrange themselves into stable structures, flowing liquids, and drifting gases. Plasmas demonstrate how those structures loosen under intense energy, creating luminous charged seas that fill stars and nebulae. At the opposite extreme, low-temperature physics uncovers forms guided almost entirely by quantum rules. Superfluids glide without resistance. Condensates merge many particles into unified waves, and superconductors allow currents to move effortlessly. These states highlight how matter reorganizes itself when motion slows to near stillness. Soft and intermediate materials show another side of this variety. Liquid crystals, gels, foams, colloids, and polymers occupy a wide middle ground where order blends with fluidity. Much of the natural world exists in these flexible forms, shifting gently in response to pressure, temperature, and time. Further afield, high-pressure environments reveal states that occur inside giant planets and collapsed stars. Metallic hydrogen, degenerate matter, neutron matter, and the early universe quark-gluon plasma emerge only in the presence of immense forces. These phases reflect how matter behaves when pushed to densities far beyond anything found on Earth. Other states arise not from extremes, but from the structure of interactions themselves. Spin ices and quantum spin liquids show how patterns can remain fluid even in deep cold. Time crystals settle into rhythms that repeat steadily. Topological materials protect their behavior through connectivity rather than composition. Hybrid light matter states such as polariton fluids and exciton condensates show how illumination and substance can blend, creating flowing patterns shaped by both. Taken together, these states illustrate a universe far more varied than everyday experience suggests. Matter does not simply exist as solid, liquid, or gas, but unfolds across a spectrum shaped by temperature, pressure, geometry, entanglement, and the quiet rules of quantum physics. Each state reveals another way particles can organize themselves when the conditions invite it. In that broad landscape, one idea stands out. Matter behavior is not fixed. It changes gently and continually, adapting to its environment with a kind of understated creativity. From glowing plasmas to drifting exciton condensates, from quantum liquids to crystalline stars, every form reflects a different balance of forces, a different way the universe expresses its structure. As this exploration settles, what remains is a sense of quiet intricacy. Matter is layered, responsive, and filled with possibilities that rarely appear at the surface. And in that variety lies a simple, calming thought. Even the smallest particles can find new ways to move, arrange, and transform when the conditions are right. A soft reminder that the universe holds more forms than can be seen, and that each one drifts gently into the next like a long exhale fading into the dark. I hope the trip was peaceful. Good night.